Hey everyone, and welcome back to the software development training program by SimpliCode. This is day 2 of the software development and we'll discuss algorithms in today's session. In case you missed out on day 1 where we discussed the fundamentals and foundation of the software development, the data structures, then please feel free to check out the cards above, and also we'll leave the link in the description box below to all our videos and playlists. Before we move ahead, I would like to take a quick confirmation from the viewers if we are clearly audible and the screen is clearly visible. If yes, kindly type yes in the chat section, and if any changes are required from our end, then please do let us know in the chat section only. Alright, I see a lot of positive responses in the chat section. So let's wait for some more minutes so that some more people can join us. Until then, let me tell you guys that we have regular updates on multiple programming videos. So if you are a programmer and if you want to learn something new, then consider getting subscribed to our YouTube channel and press that bell icon to never miss any updates from SimpliCode. Also, if you have any queries related to today's topic, then please feel free to drop them down in the comment section only, and we'll definitely address them as soon as possible. Now coming back to the topic, algorithms are known as the brain of any software program. It happens to be the baby steps of any programmer to devise the solution to a problem in a step-by-step manner. Algorithms are the main logical backbones of any software development. For example, consider maps for navigation that you use on your smart devices. We use several algorithms like the Dijkstra's algorithm, the breadth first search, depth first search, and many more to find the shortest and the most viable path to travel from the source to the destination. We have just scratched the surface and we still have a whole mountain of algorithms. We'll learn all of them and the practical implementation in detail. So stay tuned to us. Now let's get started with the agenda for today's session. Over to our training expert.
So we will begin this data structure part 2 from where we left the data structures part 1, that is trees in data structures. So followed by trees in data structures, we will be learning the tree traversal in data structures. Then we will go through binary trees, binary search trees, and then we will enter recursion. And after finishing recursion, we will begin with AVL trees. Then we will continue with B trees and B plus trees. Followed by B plus trees, we have the sorting algorithms. So we will begin with bubble sort, then we will go through insertion sort, then we have selection sort, followed by that we have heap sort, then the merge sort, quick sort, bucket sort, and counting sort algorithms. Moving ahead, we have the radix sort, followed by the sorting algorithms. We enter into graphs. And after learning the fundamentals and some examples in graphs, we will continue with Kruskal's algorithm, then the backtracking algorithm, then we have the spanning trees. Understanding the spanning trees, we will go through some breadth first search and depth first search algorithms which are used for exploring the nodes in trees. Then we have shell sort, then the greedy algorithm, and finally we have the Prim's algorithm. So I hope I made myself clear with the agenda. Now, without any further ado, let's get started with the first concept in the data structures part 2, that is trees. What is a tree data structure? So what exactly is a tree data structure? The tree is a non-linear data structure that consists of nodes and is connected by edges. I know it's a little difficult to understand just by the definition, so let me show you the pictorial representation. As you can see, we have the elements, that is 10, 20, 30, 40, 50, 60, and 70, and all these are stored in the tree data structure. They are stored in a non-linear structure. If we had used arrays, it would have been in a linear consecutive way where 10 starts first and 70 ends at the last position. Now, in the next section, we will discuss why we had made to a switch to the tree data structure when we already had a linear data structure, that is array. Now the next topic, that is why we need tree data structure. So there are many reasons why we had switched into tree data structure, and one of the reasons is a linear data structure always stores the elements in a sequential form, that is one after the other. And in operations to be performed in linear data structure, the time complexity increases as the data size increases. You can see here that, as discussed before, the elements are stored in a linear form, that is 10 at the first place and 70 at the last place. Imagine you wanted to access the element 70. Then using the traversal, you had to start from the first position, that is 10, 20, 30, 40, and slowly at the end is 70. So accessing that particular element is really time consuming. We are facing this just for 70 elements. Imagine if we had 700 elements, right? So that is exactly why we had made a switch to tree data structure. And using tree data structure, we have many advantages, as the tree data structure is completely non-linear and it allows easier access and quicker access of the data elements. How is that possible? We will look into it into the next segment, where we will discuss about the traversal of trees. Now, before we understand the traversal of trees, we should understand another important topic, that is the terminologies of tree. So the first one is the node. Node is the entity that contains the keys and pointer to its child nodes. So here you can see that the elements A, B, C, D, E, F and G are the elements. So each and every element, or the blue dot, is called as a node. And the blue dots here are 1, 2, 3, 4, 5, 6 and 7. So we have 7 blue dots. So we have 7 elements here. So you can see the line between each element, right? So this particular line is called edge. Now we'll discuss about the edge in the next part. So the connecting links between any two nodes are called as edges. So we discussed about the nodes, right, where the element is stored. The blue dots are the nodes, and the lines connecting between the elements or nodes is called as the edge. So out of all the nodes, this first node, that is the element A, is called as the root node in a tree data structure. So indirectly, root node is also called as the parent node of all the nodes. Now we will understand what are parent nodes and children nodes. So in a tree data structure, the node, that is the node's predecessor, is called as parent node. So here we have discussed that A, or the root node, is the parent of all nodes. So for A, B and C nodes are children nodes. And for B and C nodes, A happens to be the parent node. Similarly, D and E are the children nodes of B, and F and G are children nodes of C. And the nodes D and E have B as the parent node, and the nodes F and G have C as the parent node. Now followed by that, we will understand the descendant node. So as discussed before, the descendant node is the node that comes after the parent node. Here, the B and C are the descendants of A, and D and E are descendants of B, and similarly F and G are the descendants or children of the node C. So in a tree data structure, the node which does not have any child is called as the leaf node. Now at the end we have D, E, F and G. So these particular nodes do not have any children nodes like B and C. So these particular 4 nodes which do not have any children are called as the leaf nodes. In a tree data structure, the node with at least one child node is called as the internal node. So here the internal nodes are B and C, which have at least one child. In a tree, the total number of children of a node are called as the degree of that node. So in this particular diagram, the degree of a root node is 2 because it has 2 child nodes, and the degree of B is 2 as it has 2 child nodes. Similarly, the degree of C is 2 because it has 2 child nodes. But when it comes to D, E, F and G, the degree is 0 because they do not have any child nodes. In a tree data structure, the root node is said to be at level 0, and the children of the root node are said to be at level 1, and the children nodes of the level 1 are at level 2. So to understand this, let's go through the diagram. As you can see, this particular root node is called as level 0. And followed by that, we have the children nodes of A, that is B and C, and that level is called as level 1. And followed by that, we have level 2. And if this tree goes forward, the levels also increase accordingly. Now, in a tree data structure, the total number of edges from a leaf node to the particular node is the longest path, and this particular path is called as the height of that node. Now here we have our general tree data structure, and here you can see the height of node A is 2. And the height of node B and C together is at 1. And the height of the last leaf nodes happens to be 0. Next, in the tree data structure, the total number of edges from the root node to a particular node is called as the depth of that node. Now in this particular tree data structure, the depth of the root node is 0. And the depth of B and C together is 1, because the number of edges connecting to the node A from B is just 1. And similarly, the number of edges connecting the node C from A is just 1. So the depth of both B and C is 1. Now, if we consider the last leaf nodes, then the depth is 2, because if you see, G is connected to A using 2 different edges. Similarly, F is connected to A using 2 different edges, and E and D also have 2 nodes to connect to A. So the depth is 2. Now in the next segment, we will understand the tree node. So the tree data structure has data part and references towards left and right child node in the tree data structure. So here you can see this is the node, and the node has 3 segments, that is data element and the references towards left child and the references towards right child. Now there are 4 different types of trees. The first one is the binary tree, followed by that we have the binary search tree, then we have AVL tree, and finally we have the B tree. Let us discuss each one of them. The first one is the binary tree. A binary tree is a tree data structure in which each parent node at most has 2 children. So in this particular tree, we'll have at most 2 children. That means it might have 1 or more than 1, but not more than 2 children per node. Moving ahead, we have the binary search tree. So a binary search tree, or a BST, is a tree data structure in which each node has a maximum of 2 children. All nodes of the left subtree are less than the right node. All nodes on the right subtree are more than the root node. So here you can see the image, or the GIF, which represents the image of a binary search tree. So here, all the nodes of the left subtree are less than the root node, and all the nodes of the right subtree are more than the root node. The next type of the tree is the AVL tree. The AVL tree got its name after inventory Georgi, Adelson, Welsky, and Landis. AVL tree is the self-balancing tree in which each node maintains a balance factor whose value is either 1, 0, or -1. Balance factor is equals to height of the left subtree minus height of the right subtree, or height of the right subtree minus height of the left subtree. So in this particular image, you can identify it is an AVL tree. And now the last type of tree, that is the B tree. B tree is a special kind of self-balancing search tree in which each node can contain more than 1 key and can have more than 2 children. B tree is also known as the height-balanced M-way tree. Now in this particular GIF, we can see how a B tree looks like. Now followed by this, we will discuss the tree traversal. So traversing a tree helps to visit required node in the tree to perform specific operations. Tree traversal can be performed in 3 different ways. The first one is the pre-order traversal, where we visit the node and visit all the nodes from the left side, then visit all the nodes from the right side. So this particular GIF is an example for pre-order traversal, where we visit all the left side nodes first, then we visit the right side nodes. Now we will move ahead into the next type of traversal. That is the in-order traversal. First, we visit all the nodes from the left side, then we visit the root node, and then we visit all the nodes from the right side. So this particular GIF will be an example for the in-order traversal, where we visit all the left side nodes, then we visit the root node, and followed by that we will visit the right side nodes. And the last type of traversal is the post-order traversal, where we visit all the nodes from the left side first, then we visit all the nodes from the right side, and finally visit the root node. So this particular image on the right side is an example for post-order traversal. Now, before we get into learning the applications of trees, we will try to execute one example based on the post-order, pre-order, and in-order traversals in tree data structure. So you can see that we have an example on my screen right now. So here we have the node structure. Then we have the in-order traversal function. Followed by that, we have the pre-order traversal function. And finally, we have the post-order traversal function. Now let's quickly run this program and see the output. And don't worry about the code. This particular code document will be attached in the description box below and you can have access to it. Now we have the run option over here and the program got successfully executed. You can ignore this warning, and here we have the in-order traversal of the tree and the first output. Then we have the pre-order traversal of the tree, and finally we have the post-order traversal of the tree. Now let's discuss the last part where we will learn the application of trees. So the application of trees are as follows. Binary search trees are used to quickly check whether an element is present in the set or not. Then we have the most popular database usage of B-tree, which is a variant of tree data structure. Then we have the modified version of trees called as trice, which is used in the router to store routing information. And finally, the compiler uses a syntax tree to validate the syntax of every program you write.
What is tree traversal in data structure? Tree traversal is a process of visiting each and every node in a tree data structure. So right here on my screen, we have a tree with different nodes, that is A, B, C, D, and E. So here we will be visiting all the nodes one after the other using the tree traversal methods. Now that we have a brief understanding of what exactly is a tree traversal process, let's get into the next topic of our discussion for today, that is the data structure used for tree traversal. In a tree data structure, there are primarily two data structures utilized for tree traversal. The first one is the stack data structure and the second one is the queue data structure. A stack is a linear data structure that operates on the last in, first out, LIFO principle. There is only one pointer in the stack, that is the top pointer, which points to the stack's topmost element. Only the top of the stack is used for insertion and deletion. Now the next one is the queue. A queue, unlike stacks, is open on both the ends. The one end is always open and used only for input, and the other is only used for deletion or elimination. The principle followed in queue is first in, first out, or FIFO approach. Followed by that, we will look into the different types of tree traversals in data structure. Tree traversal can be done in the following ways. The first one is breadth first search and the second one is the depth first search. First, let us have a look at the breadth first search algorithm or breadth first search traversal. We follow level order traversal in breadth first search. Breadth first search traverses nodes by level instead of subtrees. First, we visit the root node. Followed by the root node, we visit the left subtree of the tree. Then, followed by the left subtree, we finish the right subtree of the entire tree. After that, we go until the leaf nodes of the entire tree is found. The second one is the depth first search. In depth first search, we traverse tree data structure in three ways, that is pre-order traversal, in-order traversal, and post-order traversal. Let us take a look at how these traversals are carried out. First, let us discuss the pre-order traversal. We traverse the root node first in the pre-order traversal. Then we traverse through the left subtree and finally we traverse through the right subtree. Then there is in-order traversal. In-order traversal involves traversing of the left subtree first, followed by that we enter the root node, then we visit the right subtree. Lastly, we have the post-order traversal. So post-order traversal involves traversing of left subtree first, then the right subtree, and finally we visit the root node. Now next, we will have a look at some of the important applications of tree traversal in data structure. So we use tree traversal in data structures to build a prefix expression or Polish notation from expression trees. Then utilize the pre-order traversal and then traverse the expression tree in a pre-orderly manner. A binary tree's postfix representation or reverse Polish notation can be generated using post-order traversal. Because it returns values from the underlying set in order, according to the comparator setting up the binary search tree in order traversal is often employed on binary search trees. A complete binary tree can be deleted or released when deleting or freezing nodes and values in the post-order traversal. Now, next we will see an example based on tree traversal in data structures.
So on my screen, we have an example for tree traversal in data structure. To begin, we have included the enum or user specified data type traversal. It mostly used to give integral constant names which make a programmer easier to comprehend and maintain. We defined three variables in the enum data type, that is pre-order, in-order and post-order traversal. We can define the type that can take one of the two values by using the typedef and enum keywords. We have a traversal data type with trav variable and a node data type with node variable. Then we define the node using the data structure type as struct node. We declare one variable x and two nodes as a left and a right nodes respectively in this node section. We then attempted to create a node using the create node function, passing the root node as an argument. In this code, we use a malloc function to create a node, assign data to x and null to both the right and left nodes before returning to the root node. If node t is not equal to null, we simply return it. Otherwise, we will use the released tree function to release the left and right nodes, and if neither is a root node, then we will use the free function to release the node t, which will behave as the root node. Then we define the display tree function, which takes the trav variable and the root node as parameters. There is a condition in this function, that is, if the root node is not null, we will return the root node. Then, using the switch case scenario, we attempted to traverse the tree using all three types of traversals. We utilize a trav variable in the switch function, so if any of the in-order, pre-order or post-order variables match the trav variable, the traversal will be executed. Then, we created a tree using the create tree function, which takes a data variable as input. In the create tree function, we used a malloc function to create the root node, and we first assigned null to the left and right nodes, as well as the data to the variable x before returning to the root node. We first traversed the root node, then the left subtree and finally the right subtree in the pre-order traversal case. In order traversal case, we first traverse the left subtree, then the root node and finally the right subtree. And in the post-order traversal case, we traverse the left subtree, then the right subtree and finally traverse through the root node. And finally, we exit the display tree function and moved on to the main function. We assign the values 5 as the root node, then 10, 20 and 30 as the left nodes, and similarly 15, 25 and 35 as the right nodes, and then we call the three tree traversals, that is pre-order, in-order and post-order, to traverse the tree. And finally, we release the root node. Now, let us try to execute this program and see the output. So there you go. The program got successfully executed and you can see that the output has been displayed on my screen. So the pre-order traversal is 5, 10, 20, 25, 15, 30 and 35. Followed by the pre-order traversal, we have the in-order traversal, that is 20, 10, 25, 5, 30, 15 and 35. And finally, we have the post-order traversal, that is 20, 25, 10, 30, 35, 15 and 5. And with that, let me give you a simple question. So what is the pre-order and post-order traversal of this binary search tree? So the elements are 1, 2, 3, 4, 5, 6 and 7. You need to find out the pre-order and post-order traversal of this binary tree and you can let us know the answer in the comment sections below. What exactly is a binary tree? So it is a tree data structure in which each node can have at most 2 child nodes. These nodes are referred to as left child node and right child node. Next, let's discuss about some terms related to binary tree. First up, a node. A node consists of data and a link to its both child nodes. Next, the root node. Root node is the first node of the tree. Next, leaf nodes. These are the nodes which has no child. Next, parent node. Apart from the root node, any node which has at least one child is called as parent to that child node. Next up, a child node. Any node with a parent is called as a child node. Next up is the internal node. Any node with a child and a parent is called as an internal node. Next up is the height of the binary tree. The longest path from the root to any leaf node is called as the height of the binary tree. Next up is the depth of the binary tree. The depth of the node is the total number of edges from the root node to the target node or the last child node. Now let's try to implement the binary tree in the code editor. As you can see, now we are on the code editor, and the code on my screen is an example for binary tree. Now here you can see that we have created a structure for node, followed by that we have a function where we will print the tree, and this is our main function. Now don't worry about the code. This particular code segment will be available in our description box below, and you can always have access to it and try to edit and run this code on your own local system to have a better learning experience. Now without further ado, let's try to run this program quickly and see the output. So there you go, the code got successfully executed, and here you can see the output of this particular binary tree. Now let's get back to the theory part. So as discussed before, followed by the implementation part, we will learn about the properties of a binary tree. Now let's discuss the properties of the binary trees. First up, maximum number of nodes at a level L is 2 to the power L. Next up, maximum number of nodes in a binary tree of height h is equals to 2 to the power of h minus 1. Next up, minimum possible height in a binary tree with 2 nodes is equals to log of L plus 1 base 2. Next up, the minimum possible level in a binary tree with n nodes is equals to log of L plus 1 base 2. Finally, a binary tree with L leaves has at least log L base 2 plus 1 levels. Now, let's discuss about the different types of binary trees. First up, we have the full binary tree. Followed by that, we have the complete binary tree. Then we have the perfect binary tree. Followed by that, we have the balanced binary tree. And lastly, the degenerate binary tree. Let's discuss about these in detail. First up, full binary tree. A full binary tree is a unique tree data structure in which a node can have either 2 children or no child. Next, a complete binary tree. So a complete binary tree is another specific binary tree where each node on all levels except the last level must have 2 children, and at the lowest level, all leaves should reside possibly on the left side. The next one is the perfect binary tree. A binary tree is perfect if every node must have 2 children and every leaf is on the same level. The next one is called as the balanced binary tree. A binary tree is balanced if for each node the height of the left subtree and the height of the right subtree varies at most by just 1. At last we have the degenerate binary tree. A binary tree is said to be degenerate if every internal node has only 1 child. We have now discussed the binary tree, some terms and properties related to binary trees, and types of binary trees. Now we will look into the operations that needs to be performed on the binary tree. So there are basically 3 types of operations that can be performed on binary tree, which are traversal, insertion, and deletion. So first we'll look into the traversal operations. There are three different types of traversal operations possible on binary tree, which are pre-order traversal, in-order traversal, and finally the post-order traversal. Now let's get back into the text editor mode and try to execute our example. So right now we are on the text editor, and this particular code is for the traversal operations on our binary tree. And here you can see we have the structure for node, and we have also the in-order function, pre-order function, and post-order function. And don't worry about the code. This particular code will be available in the description box below. And after you have written the code, we have some standard input over here. You can see that we are giving the number of edges as 4, and the left subtree elements are 2 and 1, and the right subtree elements are 2 and 3, and another left subtree elements are 3 and 5, and lastly we have 5 and 6 for another left subtree. Now let's try to execute this code. Now we have already executed the code, and we also have the output over here, and here you can see we have entered the number of edges as 4, and the traversal is in-order traversal, which is 1, 2, 6, 5 and 3, and the pre-order traversal output is 2, 1, 3, 5, 6, and the post-order traversal is 1, 6, 5, 3 and 2. Now let's get back to the PPT. Now we have the insertion operation. And now let's get back to our text editor and try to see an example for insertion operation as well. So on my screen you can see an example for insertion operation. So here we have the insert function. As I said, this particular code will be available in the description box below. Now let's provide the standard input. So the standard input will be 4 edges, and we have 2 and 1 as the left subtree, and 2 and 3 as right subtree, 3 and 5 as left subtree again, and 5 and 6 as the left subtree. Now let's quickly run this code, and there you go, the program got successfully executed, and here we have the output. The nodes got inserted, and it has provided an in-order traversal, that is 1, 2, 6, 5 and 3. Now let's get back to the presentation, and the last type of operation is the deletion operation. Let's quickly execute an example based on deletion operation as well. Now as you can see, we are on the text editor again. Now here the example is for deletion operation. We have the delete function over here. Now for this particular program we don't need any standard inputs, so just let's run the program. So there you go, the program got successfully executed, and we have the output over here. And in-order traversal before deletion, and in-order traversal after the deletion of an element. So the deleted element is element 11. Now with that, let's get back to the presentation mode again. So that's how the element got deleted. Now we have reached to the last part of this session, that happens to be the final key takeaways. So what are the final takeaways? So binary tree is faster at search operations than other type of tree, and it is easier to find maximum and minimum elements in the binary tree. Binary tree does not allow duplicate values, and graph traversal is done using binary tree. It is used to convert the postfix expressions into the prefix expressions.
Let's get started with introduction to binary search tree. Binary search tree is a set of nodes organized in such a manner that they all have the same binary search tree characteristics. A key and a value is assigned to each node. The requested key is compared to the keys in binary search tree. So during search, if the key is found, then the corresponding value will be retrieved. Next up, properties of binary search tree. First up, the left subtree of a node contains only nodes with keys lesser than the parent node. Next up, the right subtree of a node contains only nodes that are greater than the parent node. The left and the right subtree each must also be a binary search tree. Next, let's discuss what are the operations we can perform on a binary search tree. First up, insertion. Last, deletion. Let's discuss them in detail. First up, insertion. We can insert a node in such a way so that we obey binary search tree rules. That is, the new node should be either less than the parent node if it's on the left subtree, or if it's on the right subtree, it should be greater than the parent node. Let's execute this in the code editor. We will start by creating a class for the binary search tree. So class bst int data and bst pointers left, comma, right. Next, we will define some functions publicly. Public first default constructor, and a parameterized constructor. A function to insert the value. And a function to traverse the node. Now let's write default constructor's definition. So bst Now let's write the parameterized constructor's definition. Bst int value data is equals to value and left is equals to null and right equals to null. Now let's write the definition for the insert function. So bst bst star root comma int value. Now we will check if the tree is empty or not. So if root, then we will insert the first node. So we will return new bst value. Otherwise we will insert the data. So if the value is greater than root data, Then we have to insert it in the right subtree. So root right is equals to insert root right comma value. Else the value should be inserted in the left side. So root left is equals to insert root left comma value. And then we will return root. Now let's write the traverse function. So void bst traverse bst star root. If root then we will return otherwise we will first traverse left side then we will print the root data. And then we will traverse the right side root right. Now let's write the main block. So we will start with an empty tree. So bst b comma star root is equals to null. The root is equals to b dot insert root comma 50. B dot insert equals to root comma 10. B dot insert gonna be root comma 30. B dot insert gonna be root comma 50. Sorry, we already used 50, so we will use 60. B dot insert root comma let's use 20. Let's try to traverse this. So B dot traverse root. Let's execute this. As you can see, we have successfully created and traversed our first binary search tree. Let's get back to slides. At last, deletion. We will delete a node following the binary search tree rules. That is, the value of the left subtree should be less than the parent node, and the value of the right subtree should be greater than the parent node. Let's try these in the code editor. Let's start by creating a node. This time we will use structure. So struct node int key struct node star left comma star right. Now we will create a utility function to create a new binary search tree node. So struct node star new node int item. Struct node star temp equals to struct node star malloc size of struct node. Next, temp will be assigned the key is equals to item. Temp left equals to null and temp right is equals to null. Now let's write a function to traverse the tree. Traverse struct node star root. So if root is equals to null, so traverse root left cout root key traverse root right. Now let's write a utility function to insert the new node with the given key in the binary search tree. So struct node star insert struct node star node comma int key. So if node is equals to null, then we will return new node key. Otherwise, we will recur down the tree. So if key is less than the node key, then we will insert in the left subtree. So node left is equals to insert node left comma key. Else node right should be inserting key. Now let's return the node. Now we have given a non-empty binary search tree, so we have to return the node with the minimum key value found in that tree. So we will start struct node star min value node struct node star node struct node star current is equals to node. So we will loop down to find the leftmost leaf. So while current and parents left is not equals to null, so current should be equals to current to return current. Struct node star delete node struct node star root comma int key. If root equals to null, return root. Now, if the key to be deleted is smaller than the root's key, then it lies in the left subtree. So we will check if key less than root key, then root left will be equals to delete node root left key. Comma key. Now, if the key is deleted is greater than the root's key, then it lies in the right subtree. So else, if key is greater than root, root right is equals to delete node root right comma key. Else, if roots dot left equals to null and root dot right is equals to null, then return null. Else, if root left equals to null, then struct node star temp is equals to root right and free root. Return temp. Else, if roots right is equals to null, then struct node star temp is equals to root tree root return temp. Now node with the two children get the in-order successor smallest in the right subtree. So struct node star temp is equals to min value node root right. Now we will copy the in-order successors content to this node. So root is equals to temp. Now we will delete the in-order successor. So root right equals to delete node root right comma temp t. Now we will return root. Now let's write the main block. We will start with an empty tree. Struct node star root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 5 root is equals to insert root comma 3 root is equals to insert root comma 4 root is equals to insert root comma 7 and root equals to insert root comma 6. Let's try to traverse this. So cout traversal of the given tree. Traverse root. Now first we will delete a value. So cout delete 2. Now root is equals to delete node root comma 2. Now cout traversal after deleting the traverse root. Let's execute this. As you can see, we have successfully deleted 2 and traversed the tree again. Let's get back to our slides. At last, let's sum up what we have learned from this session. First up, left side nodes are always lesser than the parent's node, and the right side node are always more than the parent node. Next, it is easier to search and sort elements in a binary search tree. Finally, a binary search tree offers faster insertion and deletion operations.
What is recursion? Well, recursion is a process in which a function repeatedly calls itself either directly or indirectly. Those calls are majorly done by explicitly calling function by its name. However, it can also be accomplished by implicit calling as well. The fundamental idea behind calling the function over and over again is to break a larger problem into smaller subproblems. We do this for reducing the computational complexity of a larger problem by breaking it into several pieces. This tactic is also called as divide and conquer approach in programming. So now you must be thinking about how we can break the larger problem into smaller subproblems. Well, to do that, we break the given problem statement into two parts. The first one is base case and the second one is recursive step. The base case is nothing but the simplest instance of a problem that consists of condition which holds the recursive function. Given the function call's argument, this base case computes the output of our program right away. Whereas in the recursive step, we compute the result using one or more recursive calls to the same function, but with the inputs decrease in size or complexity. To understand this breakdown, let's have a look at mathematical aspect of recursion. Suppose you have to formulate a mathematical function for computing the sum of n natural numbers. That means the function that you are going to create must calculate the summation of all natural numbers in the range 0 to n. Mathematically, it can be represented as summation of all numbers from k is equal to 0 to k is equal to n. Now the critical question here is, how can we actually represent this in form of recursive function? The answer is quite simple. All we need to do is break this larger problem into small fragments. We can represent this problem as n plus sum of all natural numbers till n minus 1. This process of traversing in function f n minus 1 times is called the recursive step of our problem statement. Whereas the base case is a condition which is stopping the recursion when k is reaching value 0. In terms of programming, it can be represented using if block. Now I hope you guys have understood how we can break a larger problem into smaller subproblems. Moving further, we are going to understand how recursion gets executed in memory area. In order to do that, we'll take this C program as an example. In this program, we have two methods. The main method contains one variable and the statement that invokes a function named fun. This function fun is making a recursive call in its function body. We have both base case and recursive step inside this function's body. Now, whenever a function is called, its activation record will be maintained inside the stack. So, for this program, we are going to look into its control flow. As we know, the main function gets invoked primarily by an operating system. Thus, we'll include the main function at first in our memory stack. This activation record will consist of local variables of function, parameters, and the record of return address to the caller. But here, for the sake of simplicity, we are just maintaining the local variables inside the activation record. After this step, as you can see, the main function is activating method fun with argument 3. Once activated, it will prompt 3 on screen and will invoke fun3 minus 1. That is fun2. Now again, as 2 is greater than 0, the control will invoke fun2 minus 1. That is fun1. After this, the control will activate fun0. This time, once the control enters an if block, it will execute a return statement, and activation record 0 will get popped out of the memory stack. Further, every function inside the memory stack will get popped out from it, which will result in generation of output. The output that will get printed on the console for this particular program is 321. Now, here is the interesting question that we want you all to answer. Based on the properties of recursion that we have discussed till now, which of the following statements seems right to you? The options that we have are: recursion is always better than iteration. Option B. Recursion uses more memory compared to the iteration. Option C. Recursion uses less memory compared to the iteration. It will be interesting to see how many of you guys will get this right. So guys, do leave your answers to this question in comment section below. In a week's time, we'll be announcing the right answer and you all can check it out. Now moving ahead, we'll discuss different types of recursion in programming. There are basically 4 types of recursion. The first one is direct recursion, the second one is indirect recursion, the third one is tail recursion, and the fourth one is non-tail recursion. So let's discuss direct recursion. A function is called direct recursive if it calls itself in its function body over and over again. To better understand this definition, let's look at the structure of a program that is direct recursive in nature. In this program, we have a method named fun which is calling itself again and again in its function body. Thus, we can say that it is direct recursive in nature. Next up is indirect recursion. The recursion in which the function calls itself via another function is called as indirect recursion. For example, in this program, you can clearly see that the function fun1 is explicitly calling fun2, which is invoking fun1 again explicitly. Hence, we can say that this is an example of indirect recursion. Further, we have tail recursion. A recursive function is said to be tail recursive if the recursive call is the last execution done by the function. Let's try to understand this definition with the help of an example. If you observe this program, you can see that the last line ADI will execute for method fun is recursive call, and because of that, there is no need to remember any previous state of our program. Finally, we have a non-tail recursive function on our list. A recursive function is said to be non-tail recursive if the recursion call is not the last thing done by the function. After returning back, there is something left to evaluate. Let's consider one example. In this function, you can clearly observe that there is another operation after the recursive call. Hence, our ADI will have to memorize the previous state inside this memory block. That is why this program can be considered as non-tail recursive. Now finally, let's implement a program to demonstrate the recursion. The program that we are going to implement is solution to the problem statement that we discussed earlier. According to that problem statement, we have to calculate the sum of n natural numbers given the number n. Now in order to address this problem, we are going to use C programming language. So without any further ado, let's head over to the code editor. Now in order to get started with coding implementation, first we'll create an utility function to calculate sum of n natural numbers. So let's do that, and we'll pass an argument int n. Now we have arrived inside the body of function sum. What we'll first do is we'll calculate sum of n minus 1 natural numbers by making a recursive call to function sum. So let's do that. Sum n minus 1, and we'll store this value inside a temporary variable. Now we'll add this temporary variable's value to n in order to return it as a result. The statements that we just wrote are called as recursive steps. But if you observe this statement, we are not putting any limitation to our recursive call. So that is why we'll have to add base case to our function. So let's do that. If n equal to 0, then return 0. With this, we have successfully implemented our sum function. So let's work on our driver method to generate the result. In this driver method, first we'll create a variable n, and after that we'll write a printf statement. Enter the natural number n to calculate the sum of n numbers. Semicolon, and in next line we'll write scanf statement in order to take input from our user. So inside this we'll write modulus d, comma, ampersand n, and semicolon. And in next statement we'll make a call to our sum function in order to calculate sum of n natural numbers. So how we can do that? Well, we can add modulus d here, comma, sum n, semicolon, and I hope our code works fine now. So let's check it by compiling. Here the console is asking us to provide with value of variable n, and I'm going to provide value 5 here. So let's provide value 5 and enter. So the output that we are getting is 15 here. That means our code works fine.
Recursion. It is one of those topics which tends to blend with almost every other category in the programming world. Interviewers always ask questions based on recursion to gauge candidates' problem-solving abilities, because this topic pushes the candidate's limit and differentiate them between good and exceptional. In this session, we will discuss some of the commonly used recursion problems asked in the interviews. We will calculate the sum of numbers from 0 to a given number. We will start with creating a function sum. In function definition, we will first check if the given number is 0 or 1. Then we will return the number. Else, we will return addition of that number with the recursive sum function with n-1 as an argument. Now, let's try it in the code editor. We will write a function int sum, argument int num. We will check if num is equals to 0 or num is equals to 1. If yes, then we will return num, else we will return num plus sum of n minus 1. Now we will write the code for the main block. We will declare int n comma res. We will call scene to take the input data. Then we will equals res equals to sum at n. Then we will print this sum. Res. Now let's try and execute this program. We will give argument as 5. As you can see, our function is working flawlessly. Let's get back to our slides. Now let's move on to our next question. We will discuss a recursive function to find the factorial of given number. We will start with creating a function fact. In function definition, we will first check if the given number is less than or equal to 1. Then we will return 1, else we will return multiplication of that number with a recursive fact function call with n-1 as an argument. Now let's try that in a code editor. We will start with function int fact, argument int n. If n is less than equals to 1, then we will return 1. Else we will return n multiplied by recursive function fact with n-1 as argument. Now let's write the code for the main block. So we will declare variables int n comma res. We will take input from the user. Now res is equals to fact n. Now we will try to print the value of res. So factorial res. Let's try and execute this. We will find the factorial of 5, which is 120. As you can see, our function is working flawlessly. It is getting us the value of factorial 5, which is 120. Let's get back to our slides.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by SimpliLearn. Click on the link in the description to know more.
Then we will move on to our next question. We will discuss a recursive function to find the nth Fibonacci number. We will start with creating a function Fibonacci. In this function's definition, we will first check if the given number is less than or equal to 1. Then we will return that number. Else we will return the sum of recursive function Fibonacci with n-1 as an argument and recursive function Fibonacci with n-2 as an argument. Now let's try to do that in the code editor. Let's start by creating a function int Fibo with argument as int n. We will first check if n is less than equals to 1. If yes, then we will return n. Otherwise, we will return sum of recursive function fibo at n minus 1 and the Fibonacci function at n minus 2. Let's write code for the main block. We will start with variable int n, res. We will call cin function to get user value for n. Then we will store the value of Fibonacci function in res. Now we will call print function cout to print the value of res. So nth Fibonacci number is equals to res. Return 0. Let's try and execute this. We will check the Fibonacci number at 9th position, which is 34. As you can see, we are getting the value as 34. That is, our function is working flawlessly. Let's get back to our slides. Now we will move forward with our next question. We will be discussing a recursive function that can check if a string is palindrome or not. We will start with creating a Boolean function in isPalin with an argument as string str, integer low, and integer high. First, we will check if the string has at least one character or not. Then we will compare the first character and the last character. If a mismatch happens, then we will return false. Otherwise, we will move to our next pair by recalling the recursive function with incrementing low and decrementing high by 1. Now, let's try this in the code editor. We will start by creating a recursive function to check if str from low to high is a palindrome or not. Here, the low defines the first index and high defines the last index. So we will write a Boolean function is palin with argument as string str, comma int low, comma int high. We will check first our base case. So if low is greater than equals to high, then we will return now we will check if the first character is equal to the last character. Return false. Now we will move to the next pair. So return is palin with argument as str, comma low plus 1, comma high minus 1. Now let's write the code for the main block. So we will take string str is equals to Malayalam Now we will check if len, repeat. Now we will find the length of this string. So int len is equals to str dot length. Now we will check if is balin from str comma 0 to comma len minus 1. If it is true, then it will give cout. We will print palindrome else we will print not a palindrome. Let's try and execute this in the code editor. As you can see, it is saying that it is a palindrome, which is correct. So our function is working flawlessly. Let's get back to our slides. Finally, we will discuss a recursive function that can reverse a given string. We will start with creating a function reverse with an argument as string str, integer low and integer high. First, we will check if the string is greater than 1 character or not. If yes, then we will swap them. Then we will move to our next pair by calling the recursive function reverse with incrementing low and decrementing high by 1. Now let's try this code in the code editor. We will start with creating a recursive function, but before that we will include a special library include algorithm. Now void reverse string and %str. Note that we have passed the string as a reference parameter. Int low, int high. Now we will check if low is less than high. If yes, then we will swap str at low, comma str at high. Then we will call the recursive function reverse to move to our next pair str, comma low plus 1, comma high minus 1. Let's write code for the main block. We will write string str, which is equals to SimpliLearn. Now we will reverse str, comma 0, comma str dot length minus 1. Now cout reverse of the string str equals to str. Let's try and execute this. As we can see, this function is working flawlessly as it has reversed the word SimpliLearn. An ABL tree is a height balanced binary search tree. For each node, we have to make sure that the height of the left subtree and the right subtree can differ by at most 1. We can calculate this balance factor by subtracting the height of the left subtree from the height of the right subtree. Now let's discuss various rotations we can perform on ABL trees. First up, LL rotation. Next, RR rotations. Next, LR rotation. At last, RL rotation. Let's discuss them in detail. First up, LL rotation. It is a clockwise rotation when a node is inserted on the left subtree of a node. Then we apply this rotation to balance the tree. It is applied on the node below the balance factor 2 node. That is, we will apply right rotation on the green node. Next, RR rotation. When a node is inserted into a right subtree of a node, then we perform RR rotation. It is an anti-clockwise rotation which is applied on the node below a node having balance factor -2. That is, we will apply it on the green node. Next up, LR rotation. When a node is inserted into right subtree of the left subtree of a node, then we perform LR rotation. It is a combination of RR and LL rotation. First, we will apply RR rotation on green and yellow node. After this, red node is still unbalanced, so we will perform LL rotation on the yellow node. Finally, RL rotation. When a node is inserted into the left subtree of a right subtree of a node, then we perform RL rotation. It is a combination of LL and RR rotation. First, we will apply LL rotation on green and yellow nodes. After this, the red node is still unbalanced, so we will perform RR rotation on the yellow node. Now let's discuss complexity of ABL trees. First up, space complexity is a big O of n. Next up, ABL tree offers a complexity of big O of log n for searching. Next up, ABL trees offer a complexity of big O of log n for insertion. Finally, ABL tree offers a complexity of big O of log n for deletion. We have now introduced an ABL tree and rotations on it. Now let's discuss some of the operations we can perform on ABL trees. First up, insertion and deletion. Let's discuss them in detail. First up, insertion. We will insert a node following binary search tree rules. Then we will check if the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor. Let's start by creating a node. To create a node, we need a class node. We will create its member as public. Int key node star left node star right. Int height. Now let's write a function to get maximum of two integers. So int max int a comma int b. Now let's declare a utility function to get maximum of two integers. So int max a comma int v. Now let's write a function to get the height of the tree. Int height node star n. Now if n is null, then we will return 0. Else we will return n calls height. Now let's write that function to get maximum of two integers. Int max int a comma int b. We will return if a is greater than b, then we will return a, else we will return b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. Node star node equals to new node. So node key will be equals to key node left will be equals to left. Node left will be equals to null and node right will be equals to null and node height will be equals to 1. And return node. Here we have kept height as 1 because at the new node is initially added at leaf. So by default it will always be at 1. Now let's write a utility function to right rotate subtree rooted with y. Node star right node star y. Now node star x is equals to y's left and node star e2 is equals to x right. Now we will perform rotation. So x right will become y and y's left will become T2. Now we will update the heights. So y height is equals to max of height of y left comma height of y right plus 1. Now x height equals to maximum of height x left comma height of x right plus 1. Now return x. Now let's write a utility function to left rotate subtree rooted with x. So node star left rotate node star x node star y will be equals to axis right and node star t2 will be equals to axis y's. Now we will perform rotation. So y left will be equals to x and x right will be equals to t2. Now let's update height. So x height is equals to maximum of height of axis left comma height of axis right and y's height equals to maximum of height of y's left comma height of y's right. Return y. Now let's write a function to get balance vector of node n. So int get balance argument as node pointer n. if n is equals to null, then we will return 0. Otherwise, we will return height of n's left minus height of n's right. Now let's write a recursive function to insert a key in the subtree rooted with node and returns the new root of the subtree. So node star insert node star node comma int key. Now we will perform the normal BST insertion. So if node is equals to null, then we will return new node key. Now if this key is less than node's key, then node left will equals to insert node left comma key. Or else we will insert that in the right. Node right is equals to insert node right comma key. Now we will return node. This if else will make sure that we will reach to the leaf node and then we will insert the key. Now we will update the height of this ancestor node. So node height is equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor for this ancestor node to check whether this node became unbalanced. So int balance is equals to get balance Now if this node becomes unbalanced, then there are 4 cases. So if balance is greater than 1 and key is less than node left key, then we will return right rotate node. This if statement for the left case, so or LL case. Now let's write it for the right case or RR case. So if balance is less than -1 and P is greater than node right key, then we will return left rotate node. Now write for the left right case or LR case. So if balance is greater than 1 and key is greater than node left key, then node left is equals to left rotate node left. Now return right rotate. Now let's write the right left case or RL case. So if balance is less than -1 and key is less than node to the right key, then node right will be equals to right rotate node to the right, and we will return left rotate. Now we will return this node. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root. So now if root is not null, then cout root key and now pre-order root and pre-order. Now let's write the code for the main block. We will start with an empty tree. Node star root is equals to null. Now we will try to construct tree. So root is equals to insert root comma 10. Now root is equals to insert root comma 5. Root is equals to insert root comma 2. Root is equals to insert root comma 3. Root is equals to insert root comma 7 and root is equals to insert comma 9. Now let's try to print this tree. So cout avial tree is equals to tree in tree order tree order root. Let's execute this. As you can see, we have successfully created our first avial tree. Let's get back to slides. At last, deletion. We will delete a node following a binary search tree rules. Then we will check if all the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor. Let's start by creating a node. To create a node, we need a class node. We will define its members as public int key node star left node star right int height now let's write a utility function to get height of the tree. So int height node star n. If n is equals to null, then in that case we will return 0. Otherwise we will return n's height. Now let's write a utility function to get maximum of two integers. Int max, int a, comma, int b. So we will return if a is greater than b, then a, else b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. So node star new node is equals to new node parenthesis. Now new node will get key as key. New node left is equals to null, and new node right is equals to null, and new node's height is equals to 1, because new node is initially added as leaf. That's why it is always be given as 1. Now we will return this node. Return node. Now let's write a utility function to right rotate a subtree rooted with y. So node star right rotate node star y node star x is equals to y left node star t2 is equals to x right. Now we will perform rotation. So x right is equals to y left is equals to t2. Now we will update heights. So y height equals to maximum of height of y's left, comma, height of y's right plus 1, and x height is equals to maximum of height of x's left, comma, x's right plus 1. Now we will return this new root. So return x. Now we will write node star left rotate node star x node star y will be equals to axis right and node star t2 will be equals to y's left. Now we will perform rotation. So y left equals to x and x right is equals to t2. Now we will update these heights. So x height is equals to maximum of height of x left comma height of x right plus 1 and y's height is equals to max of height of y's left comma height of y's right plus 1. Now we will return this y. Now we will write a function to get balance factor of node n. So int get balance node star n. So if n is equals to null, then we will return 0. Otherwise we will return height of n's left minus height of n's right. Now let's write a function to insert a node. So node star insert node star node comma int key. Now we will perform normal BST rotation. So if node is equals to null, then we will return new node key. So now if key is less than node key, then node left will be equals to insert node left comma key. Now if key is greater than node key, then node right is equals to insert node right comma key. Else we will return node because equal keys are not allowed. Now we will update the height of the ancestor node. So node height equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor of this ancestor node to check whether this node becomes unbalanced. So if int balance equals to get balance of this node. Now if this node becomes unbalanced, then there are 4 cases that could be possible. First up, LL case. So if balance is greater than 1 and key is less than node left key. Return right rotate node. Now let's write right case. So if balance is less than -1 and key is greater than node right key, then we will return left rotate node. Now let's write left right case. So if balance is greater than 1 and key is greater than node left key, then node left will be equals to left rotate node and we will return right rotate node. Now let's write the case for right left case. If balance is less than -1 and key is less than node right. So node right is equals to right rotate node right. Now we will return left rotate node. Now let's return the unchanged node pointer. So return node. Now let's write a function to find minimum value node. So node star min value node. Node star node. So node star current equals to node. So while current left is not equals to null, current is equals to current at left. Now we will return current. Now we will write a recursive function to delete a node with the given key from subtree with the given root. So node star delete node. Its arguments are node pointer root, comma, int key. For starters, we will perform standard BST delete. So if root is equals to null, then we will return root. Now, if the key to be deleted is smaller than the root key, then it lies in the left subtree. So, if key is less than root key, then root left will be equals to delete node root to the left, comma, key. Now, if key to be deleted is greater than the root key, then it lies in the right subtree. So else if key is greater than root key, then root right equals to delete node root right comma key. Now if the key is same as the root key, then this is the node to be deleted. So else if root left equals to null or root to the right is equals to null, then node star temp is equals to root left now if temp is equals to null, then temp will be equals to root and root will equals to null. Else root will be equals to star temp and free temp. Else node star temp is equals to min value node root right. Now we will copy the in order successors data to this node. So root e is equals to temp key. Now we will delete this in order successor. So root right is equals to delete node root comma temp key. Now if root is equals to null, Then we will return root. Now we will update the height of the current node. So root height is equals to 1 plus max of height of roots left, comma, height of comma height of root right. Now we will get the balance factor of this node. So int balance is equals to get balance root. If this node becomes unbalanced, then there are 4 cases. First up, LL case. So if balance is greater than 1 and get balance of roots left is greater than equals to 0, then we will return right rotate. Now if balance is greater than 1 and get balance of root left less than 0, then root left will equals to left rotate root left. Now we will return right rotate root. Now let's write right case. So if balance less than -1 and get balance is less than equals to 0, then we will return left rotate now we will write right left case. So if balance is less than -1 and get balance of root right is greater than 0, then root right is equals to right rotate of root right. Now we will return left rotate and we will return this root. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root. So if root not equals to null, then cout root e a pre-order root left and pre-order root right. Now let's write a code for the main block. We will start with an empty tree. So node root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 10 root is equals to insert root comma 9 root is equals to insert root comma 7 root is equals to insert root comma 5 root is equals to insert root comma 3. Now let's try and print this evil tree. So cout created AVL pre-order pre-order now we will delete a node. So root is equals to delete node root comma 10 Now let's again try and print this. So see out modified behavior tree pre-order after deletion of 10. Layout handle pre-order root read. Now let's execute this. As you can see, our deletion function is working perfectly. Now let's get back to our slides. At last, let's sum up what we have learned from this session. First up, AVL trees is a self-balancing binary search tree. Next, every node must have a balance factor of either -1, 0 or 1. Next, after every rotation, we must verify if each node is balanced or not. Finally, AVL trees offers fast insertion and deletion operations.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by SimpliLearn. Click on the link in the description to know more.
Let's get started with what is B-tree. A B-tree is a special M-way tree data structure. A B-tree of order M can have at most M-1 keys and M children. Now, let's discuss some properties of B-trees. First up, every node in a B-tree can have at most M elements. Next, every node except the root and the leaf node must have M/2 children. Next, a root node must have at least 2 nodes. At last, a leaf node must be at the same level. Now, let's discuss what are the various operations we can perform on a B-tree. We can perform 3 operations on a B-tree, that is, searching, insertion, and deletion. Let's discuss these in detail. First up, searching. In this, we will traverse the complete B-tree until we have found a key. We will start from the left side to go all the way up to the right side. Now, let's try this in a code editor. We will first start by creating a B-tree node. To do that, we will use class B-tree node int keys. It is an array of keys. Then int t. This will define the range of the number of keys. Then we will create a child pointer B-tree node. See, it is an array of child pointer. Then a variable to check the current number of keys, and a boolean variable which will be true when the node is leaf. Now define some functions in public. First, constructor. Then a function to insert a new key in a subtree, void insert non-full, argument as int k. Next, a utility function to split the child y of the node, argument as int I, comma, a b-tree node pointer y, a function to traverse the b-tree, and a function to search a key in the subtree. It will return null if key is not present. Now we will create another class b-tree and make it a friend of this so that we can access private members of this b-tree of this class in b-tree function. Now we will create a pointer root minimum degree, then public a constructor b-tree, root equals to null, and t is equals to underscore t. Now we will write a function to traverse this tree, void traverse if not null, then root traverse. Now we will write a function to search a key in this tree. Return if root is equals to null, then null, else root search. Now the main function that inserts the new key in this B tree, void insert int k. Now we will write the constructor for B tree node class. Now we will copy the given minimum degree and leaf property. Now we will allocate the memory of the maximum number of possible keys and the child pointer. And c equals to new B tree node star bracket 2 star t. Now we will initialize the number of keys as 0. Now let's write the function to traverse all node in the subtree rooted with this node. There are n keys and n plus 1 children. To traverse through n keys and first n children's, we need to do int I for loop I is equals to 0, I less than n, I plus plus. If this is not leaf node, then before printing key, traverse the subtree rooted with child ci. So if leaf is equals to false, then c bracket I will equals to traverse else c out case. Now we will print the subtree rooted with the last node. So if leaf is equals to false, and c I traverse Now we will write the function to search key k in subtree rooted with this node. So b tree node are b tree node search print k we will first find the first key greater than or equal to k. So while int I is less than n and k is greater than is bracket I, then I plus plus. Now if we found the key is equals to k, then we will return this node. If bracket I is equals to k, then we will return if key is not found here and this is the leaf node, then if leaf is equals to true, then we will return null. Now we will try to go to the appropriate child. So we will use return c bracket I arrow search. Now we will write the main function that inserts the new key in this V tree. So void B tree insert int k. So if root is equals to null. Then we will allocate the memory for root. Now root keys bracket 0 is equals to k. Now we will change root here we are updating the number of keys in this root. Now if else if tree is not empty, then if root is full, then tree grows in height. So if root arrow n is equals to 2 star t minus 1, then we will allocate the memory for the new root b tree node star s equals to new b tree node t comma false. Now we will make the old root as child of the new root. So s arrow c bracket 0 is equals to root. Now we will split the old root and move one key to the new root. So s split child zero comma root. Now new root has two children. We have to decide which of the two children is going to have a new key. So int I is equals to 0 if if as keys 0 is less than k, then I plus plus, and as arrow c bracket I arrow, insert non full k. Now we will change the root equals to s, else if root is not full, we will call the insert non-full. Now we will write a function insert for non-full will initialize int I is equals to n minus 1 if if is equals to true, then while I is greater than equals to 0 and is greater than k, then keys I plus 1 will be equals to keys I and I minus minus. Now we will insert the new key at the found location. Else while I is greater than equals to 0 is I is greater than k, then I minus minus. Now we will see if the found child is full. If c bracket I plus 1 L is equals to 2 star t minus 1, then we will use split child I plus 1 comma c I plus 1. Now if keys bracket I plus 1 is less than k, then I plus plus c I plus 1 insert non-full k. Now we will write the function split child. Y comma leaf then z and equals to t minus 1 now for loop and j is equals to 0 j less than t minus 1 j plus plus z equals to j equals to y Now we will copy the last t children of y to z. If y leaf is equals to false, then for int j is equals to 0, j less than t and j plus plus Now we will reduce the number of keys in Y. Since this node is going to have a new child, we will create a space for the new child. So for loop int j is equals to 9, j is equals to n, j greater than equals to I plus 1, j minus minus c bracket j plus 1 equals to c bracket j. Now we will link the new child to this node. Now a key of y will move to this node and find the location of new key and move all greater keys one space ahead. Now we will increment the count of keys in this node. Now let's write the main block. We will define a B tree with minimum degree 3. Now t dot insert ten, t dot insert 20, t dot insert 5, t dot insert 6, t dot insert 12, t dot insert 30, t dot insert 7, and t dot insert 17. Now let's try to traverse this. Cout traversal of B tree. And t dot traversal Now let's search some keys. So let's take int k is equals to 6. So if t.search k is not null, then cout else cout not present. Let's try this function one more time. With k is equals to 15. Let's execute this. As you can see, we have successfully traversed this B tree and we have checked two keys if they are present or not. The k is equals to 15 was not present and k is equals to 6 was present. Let's get back to our slides. Next up, insertion. We have to insert an element in such a way so that we won't disobey any properties of B trees. Now let's try this operation in a code editor. We will start by creating a node. To do that, we will use class bTreeNode. Then we will create an array of keys minimum degree, an array of child pointers, current number of keys, and a boolean variable leaf. This variable will tell if the node is leaf or not. Then we will define some public functions. We will start with constructor. Now we will create a function to insert a new key into the non-full node. A utility function to split the child, a function to traverse the tree, a friend class bTree, Now we will create this class btree. Now we will define a pointer to root node, minimum degree, then we will create some public functions. First constructor, root equals to null and t equals to underscore t. Now void traverse now if root is not equals to null, then root arrow traverse. Now we will define a main function that inserts a new key in this B tree. Now we will write the constructor for the btree class. Int t1, comma, boolean leaf 1. Now we will copy the given minimum degree and leaf property. Now we will allocate memory of maximum number of possible keys and child pointers. Now we will initialize the number of keys as 0. Now let's write a function to traverse all nodes in the subtree. Now there are n keys and n plus 1 children, so we will traverse through n keys and first n children. So int I for loop I is equals to 0, I less than n, and I plus plus. Now, suppose if this is not leaf, then before printing key, we will traverse the subtree rooted with this child. So, if leaf is equals to false, then C, I, arrow, traverse. Now, we will print these keys. Now we will print the subtree rooted with the last child. So if leaf is equals to false, then Ci arrow traverse. Now we will write the main function that inserts a new key in this B tree. Void B tree int k. Now if tree is empty, then we will allocate the memory to root. So root is equals to new B tree node key, comma true. Now we will insert the key root arrow keys equals to k, and we will update the number of keys in root. So root arrow n equals to 1. Else if tree is not empty and if root is full, then tree will grow in height. If root arrow n is equals to 2 star t minus 1, now we will allocate the memory of new root. Now we will make old root as child of new root. Is equals to root. Now we will split the old root and move one key to the new root. So to do that, we will use split child function. 0, comma, root. Now new root has two children now. We have to decide which of the two children is going to have new key. So to do that, we will use int I is equals to 0 if s keys zero is less than k, then I plus plus and s arrow c I are non-full. Now we will change the root. Else root insert non-full k. Now we will write a utility function to insert a new key in this node. We will assume the node must be non-full when this function is called. So void btree node insert non-full int k. We will initialize index as index of rightmost element. So int I is equals to n minus 1. Now if this is a leaf node, then the following loop does two things. A. Finds a location of new key to be inserted, or move all greater keys to one place ahead. So while I is greater than equals to 0 and is I is greater than k, now keys I plus 1 will be equals to keys at I and I minus minus. Now we will insert the new key at the found location. So keys at I plus 1 will be equals to k and n equals to n plus 1. Now else if this node is not leaf, then we will find the child which is going to have the new key. So while I is greater than equals to 0 and keys I is greater than k, then I minus minus. Now we will see if the found child is full. So if c I plus 1 arrow n is equals to 2 star t minus 1, Now if the child is full, then we will split it. So split child at I plus 1, comma C I plus 1. After split, the middle key of Ci goes up and Ci is splitted into 2. Now we will see which of the following will have the new key. If keys I plus 1 is less than k, then I plus plus C I plus 1 insert non-full k. Child int I, comma a tree node. Now we will create a new node which is going to store t minus keys of y. So b tree node star z equals to new b tree node y arrow t, comma y arrow leaf. Now z arrow n is equals to t minus 1. Now we will copy the last t minus 1 keys of y to z. So for loop int j is equals to 0, j less than t minus 1, j plus plus. So z arrow is j equals to y arrow is j plus t. Now we will copy the last t children of y to z. So if y leaf is false, so for int j is equals to 0, j less than t and j plus plus, so z cj is equals to y c j plus t. Now we will reduce the number of keys in y. So y arrow n is equals to t minus 1. Now, since the node is going to have a new child, we will create the space for the new child. So for int j is equals to n and j is greater than equals to I plus 1 and j minus minus c j plus 1 will be equals to cj. Now we will link the new child to this node. So c bracket I plus 1 equals to z. Now a key of y will move to this node. So we will find the location of new key and move all greater keys one space ahead. So for int j is equals to n minus 1, j greater than equals to I, j minus minus is j plus 1 equals to is j. Now we will copy the middle key of y to this node. So keys bracket I is equals to y arrow keys at t minus 1. Now we will increment the counts of key in this node. So n equals to n plus 1. Now we will write a driver program to test above functions. Now we will write the main block. We will start with a B tree with minimum degree 3. Now we will insert keys in this tree. So t dot insert 10, t dot insert 15, t dot insert 5, t dot insert 6, t dot insert 12, t dot insert 7. Now let's print this constructed tree. So cout created B tree s. Now t dot traverse. Now let's execute this. As we can see, we have created a B tree of order 3. Let's get back to our slides. Finally, deletion. While deleting any elements from B tree, we have to be careful not to break any properties of the B tree. Like all the leaves must be present at the same level or elements must be in ascending order. Now let's try this operation in a code editor. Let's start by creating a node. To create a node, we need a class node int star keys. This is an array of keys. Int t, a minimum degree. Now we will define an array of child pointers. So B tree node current number of keys int n, a boolean variable leaf to tell us if the node is leaf or not. Now we will define some public functions. We will start with the constructor to this class B tree node int underscore t comma boolean underscore leaf and a function to traverse the all nodes in the subrooted tree. So void traverse. Now a function to search a key in the subtree. So B tree node star search int k. This will return null if k is not present. Now we will write a function that returns the index of the first key that is greater or equal to k. So int find key int k. Now we will write an utility function to insert a new key in this subtree rooted with this node. We will be assuming the node must be non-full when this function is called. So void insert non-full as argument as k. Now we will write a utility function to split the child of y of this node. Void split child int I comma b tree node star y. A wrapper function is to remove the keys k in subtree rooted with this node. So void remove int k. Another function to remove a key present in the ith position in this node, which is a non-leaf node. So void remove from non-leaf int idx. Now we will write a function to get the predecessor of the key where the key is present in the idx position in the node. So int get pred int idx. Now we will write a function to get the successor of the key where the key is present in the idx position in the node. So int get successor int idx. Now we will write a function to fill up the child node present in the idx position in the C array if that child has less than t-1 keys. So void fill int idx. Now we will write another function to borrow a key from the C idx-1 node and place it in C idx node. So void borrow from rev int idx. A function to borrow a key from the idx+1 node and place it at the idx node. So void borrow from next int idx. Void merge idx. Now we will make B-tree class as friend so that we can access private members of this class in the B-tree functions. So friend class B-tree. So class will start with the pointer to the root node. So B-tree node star root int t. Now we will write some public functions. We will start with the constructor. So B-tree int underscore t. So root is equals to null and t is equals to underscore t. Now a traverse function void traverse. So we will check if root is not null. Then root arrow traverse. Now we will write a function to search a key in this tree. So b tree node search int k. We will return if root is equals to null. Then we will return null. Else root arrow search at k. Now we will write the main function that inserts a new key in this B tree. So void insert int k. Now another main function that removes the new key in this B tree. So void remove int Now we will write the constructor for this B tree node class. Int t1 comma bool leaf 1. So t will be equals to t1 and leaf will be equals to leaf 1. Now we will allocate memory for the maximum number of possible keys and child pointers. So keys is equals to new int bracket 2 star t minus 1 and child c is equals to new b tree node star bracket 2 star t. Now we will initialize the number of keys as 0. So n is equals to 0. Now we will write a utility function that returns the index of the first key that is greater than or equal to k. So int b tree node find key int k. Now int idx is equals to 0, then while idx is less than n and keys idx is less than k plus plus idx return idx. Now we will write a function to remove the key k from the subtree rooted with this node. So void btree node remove int k int idx equals to find key k if the key to be removed is present in this node, then if idx is less than n and keys at idx is equals to k, now if node is leaf node, then we will remove from leaf node is called, otherwise remove from non-leaf function is called. So if leaf then remove from leaf idx, else remove from non-leaf idx. Now else if this node is a leaf node, then the key is not present in this tree. So if leaf cout k is does not exist in this tree, and return the key to be removed is present in this subtree rooted with this node. The flag indicates whether the key is present in this subtree rooted with the last child of this node. So bool flag is equals to idx equals to n if it is true, else false. If the child where the key is supposed to exist has less than t keys, then we fill that child. So if c at idx n is less than t, then fill idx. Now if flag and idx is greater than n, then c idx minus 1 remove a, else c idx remove a. Return void b tree node remove from leaf int idx. Now we will move all the keys after the idx position one place backward. So for loop int I is equals to idx plus 1, idx plus 1, I less than n, I plus 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 I. So keys at I minus 1 should be equals to at I, and we will reduce the count of keys. So n minus minus, then return. Now we will write the function to remove the idx key from the node which is non-leaf node. So void b tree node remove from non-leaf int idx. So int k is equals to keys at idx If the child that precedes k at CIDX has at least t keys, then we will find the predecessor pred of k in the subtree rooted at CIDX. We will replace k by predecessor recursively and delete pred in CIDX. So if CIDX arrow n is greater than equals to t, then int pred equals to get pred idx keys idx equals to pred c idx remove pred else if c at idx plus 1 arrow n is greater than equals to t, then int suck is equals to get suck idx. Now keys at idx is equals to suck c at idx plus 1 uses remove suck else we will merge idx and c at idx will call remove c at idx will call remove return. Now we will write a function to get predecessor of keys idx. So int btree node get pred int suck repeat int idx so btree node star cur is equals to c at idx while cur is not a leaf then cur will be equals to cur arrow C calls N. Now we will return cur key. Now we will write int b-tree node get suck int idx cur equals to c idx plus 1 while cur arrow while cur is not leaf, cur is equals to cur bracket 0. Now we will return cur Now we will write a function to fill child CIDX which has less than t minus 1 keys. Void b-tree node fill int idx if if the previous child C idx minus 1 has more than t minus 1 keys, then we will borrow a key from that child. So if idx is not equals to 0 and C at idx minus 1 calls n greater than equals to t, then we will borrow from prev idx else if idx is not equals to n and C at idx plus 1 calls n greater than equals to 1 t, then we will borrow from next at idx else
If idx is not equals to n, then we will merge idx, else merge idx minus 1, return Now we will write a function borrow from prev. Iterate node star child is equals to c idx iterate node star sibling is equals to c idx minus 1. Now the last key from c idx minus 1 goes up to the parent, and key idx minus 1 from parent is inserted as the first key in c idx. Thus the lossless sibling 1 key and child gains 1 key, moving all keys in c idx one step ahead. So for loop int I is equals to child at n minus 1 I greater than equals to 0 and I minus 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 I. Child calls keys at I plus 1 equals to child calls keys at I. Now if CIDX is not a leaf, then we'll move all its child pointers one step ahead. If underscore child calls leaf, or int I equals to child and I greater than equals to 0, I minus minus I, child at C bracket I plus 1 equals to child C bracket I. Now we will set the child's first key equal to the key at idx minus 1 from the current node. So child is at 0 is equals to keys at idx minus 1. Now we will move siblings last child as CIDX's first child. So if child is not leaf, then child arrow C bracket 0 is equals to sibling at C sibling calls n. Now keys at idx minus 1 will be equals to sibling keys sibling calls n minus 1. Now child at n will be plus equals to 1 and sibling n will be equals to minus equals to 1. Return void b tree node borrow from next int idx Now we will start by b tree node child is equals to c at idx and b tree node sibling is equals to c at idx plus 1. Now key idx is inserted as the last key in the C idx. So child keys and is equals to keys at idx. Now child at keys x. If child is not leaf, child c equals to sibling at c0. Now the first key from sibling is inserted into key idx. So key at idx is equals to sibling keys 0 for loop and I is equals to 1. I less than sibling at n plus plus I sibling I minus 1 is equals to sibling now if sibling is not leaf, for loop I equals to 1 less than equals to sibling calls n plus plus I calls c at I minus 1 equals to sibling calls C at I. Now we will be increasing and decreasing the key count of CIDX and CIDX plus 1 respectively. So child at n is plus equals to 1. Sibling calls n minus equals to 1. Return now void b tree node merge with argument as int idx b tree node star child is equals to c idx b tree node star sibling equals to c at idx plus 1. Now we will be pulling a key from the key node and inserting it at t minus 1th position in CIDX. So child calls keys t minus 1 is equals to keys at idx. Now we will be copying keys from CIDX plus 1 to CIDX at the end. So for int I is equals to 0, I less than sibling equals n, and plus plus I. So child I plus t equals to sibling I. If not child calls leave for I is equals to 0, I less than equals to sibling calls plus plus I, child calls C bracket I plus t equals to sibling calls bracket I. Now for int I is equals to idx plus 1, I less than n plus I minus 1 is equals to keys at I. For int I is equals to idx plus 2, I less than equals to n and plus I key at I minus 1 is equals to C at I child n plus equals to sibling n plus 1 delete sibling return. Now we will write the main function that inserts a new key in this B tree. So void B tree int k if root is equals to null, then we will allocate memory to root is equals to new B tree node t comma true root is bracket 0 is equals to k and root at n is equals to 1 else if root calls n is equals to 2 star t minus 1. So B tree node star s is equals to new B tree node T, comma false. Now S C bracket 0 is equals to root S split child 0 comma root int I is equals to 0 if S keys bracket 0 less than K I plus plus S C bracket I insert non-full K. Now we will change the root to S. Else root calls insert non-full at K. A utility function to insert at non-full node. So int I is equals to n minus 1 if leaf equals to true. The following loop does two things: finds the location of key to be inserted or moves all greater key to one place ahead. So while I is greater than equals to 0 and keys at I are greater than K, then keys at I plus 1 will be equals to keys at I and I minus minus. Keys at I plus 1 will be equals to K and n will be equals to n plus 1. Else while I is greater than equals to 0 and keys at I is greater than K, I minus minus if C bracket I plus 1 at n equals to 2 star T minus 1 let child I plus 1 comma c I plus 1 if is bracket I plus 1 k I plus plus c bracket I plus 1 insert non-full k void b3 node int I comma b3 node star y b3 node star z is equals to new b3 node argument as y calls t and y calls leaf. Now z calls n equals to t minus 1. Now we will copy the last t minus 1 keys of y to z. So for loop int j is equals to 0, j less than t minus 1, j plus plus, so z keys j is equals to y at keys j plus t. So if y if equals to false, for int j is equals to 0, j less than t, j plus plus, j c bracket I is equals to y calls c bracket j plus t. Now y calls n equals to t minus 1. Now since this node is going to have a new child, we will create space for the new child. So for loop int j is equals to n, j greater than equals to I plus 1, j minus minus, c bracket j plus 1 equals to c bracket j. Now c bracket I plus 1 is equals to C bracket J C bracket I plus 1 is equals to Z. Now for loop, int J is equals to N minus 1, J greater than equals to I, J minus minus is bracket J plus 1 equals to keys at J is I equals to Y is bracket T minus 1 N is equals to N plus 1. Now we will write function for traverse. So void btree node traverse int I for loop I is equals to 0, I less than N, I plus plus. If leaf equals to false, then C bracket I will traverse if leaf is equals to false, then Ci will call traverse function. Now we will write the function to search key in the subtree rooted with this node. So btree node star btree node search int k int I is equals to 0 while I is less than N ampersand k is greater than keys bracket I, so I plus plus. Now if keys bracket I is equals to k, then return this. Now if is equals to true, then return null. otherwise return C bracket I calls search for K. Now we will write the utility function to remove. So void tree remove int K. If not root, then cout the tree is empty. Return. Now we will call the Now we will call the remove function for root. So root calls remove K. Now if root has 0 keys, then we will make its first child as a new root. If it has a child, otherwise set root as null. So if root n is equals to 0, then b tree node star tmp equals to root. If root leaf root equals to null, else root equals to root C bracket 0. Now delete MP. Return. Now we will write the code for the main block. We will start with B tree of order 3. Now let's traverse this created tree. Cout created tree now cout and L now we will use t dot remove to remove 5. Now cout modified b tree after deleting 5. T dot traverse. As you can see, we have successfully deleted 5 from our B tree. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, all the operations on B tree have time complexities of log n. Next, all the leaves must be on the same level. Next, elements of B tree are sorted in ascending order from left to right. Finally, every node contains one more pointer than the number of elements of the node. Let's get started with what is a B plus tree. A B plus tree is a special m-way tree data structure. A B plus tree of order m can have at most m-1 keys and m children. A B plus tree can be used as B tree with only keys to each node and with linked leaves to which an additional level is added at the bottom. Now, let's discuss some properties of B plus trees. First up, every node in B plus tree can have at most m elements. Next, every node except the root and the leaf node must have m by 2 children. Next, maximum keys for any node is m-1. And at the last, minimum keys for any node is ceiling of m by 2 minus 1. Now, let's discuss what are the various operations we can perform on B plus tree. We can perform two operations on a B plus tree. First up, insertion. Second, deletion. Now let's discuss these in detail. First up, insertion. We have to insert an element in such a way so that we won't disobey any properties of B plus trees. Now let's try this operation in a code editor. We will start by creating a node. To create a node, we need a struct B plus tree node int star data B plus tree node space star child ptr boolean leaf and int n. For the object, star root will be equals to null star np pointer will be equals to null comma star x will be equals to null. Now we will write a constructor for it. So b tree node star init int I and p equals to new b plus tree node and p arrow data is equals to new space int bracket 5 and np child ptr is equals to new b plus tree node star bracket 6 and belief is equals to true and np at the n is equals to 0. Now we will write a for loop I is equals to 0, I less than 6, I plus plus, np child is equals to return traverse b plus tree node star p out and I again a for loop from I equals to 0 to I less than p at n I plus plus if p doesn't have leaf then we will traverse that child traverse p child ptr bracket I see out p data at I now we will check these conditions again for I at p at n we will traverse it again from P child at I. C out and L. Now next function will be used to sort this. So void sort int star p comma int n int I comma j comma temp for loop j equals to I, j less than equals to n, j plus plus. If p bracket I greater than p bracket j, then we will swap these two. So temp will store p at I and then p will replace its value with p at j. Now we will store the temp value in the p of j. Now let's write a function to split these child. Int split child p plus tree node star x comma int I int j mid b plus tree node star np1 comma star np3 comma star y. np3 is equals to init np3 equals to true. If I is equals to -1, mid is equals to x data bracket 2 x data bracket 2 will be equals to 0. Then x will store n minus minus. P1 is equals to init now when P1 leave will be equals to false and x leave is equals to true. So for loop j is equals to 3, j less than 5, j plus plus. J minus 3 will be equals to x data at j. MP3 child ptr at j minus 3 is equals to x at child ptr bracket j np3 n plus plus x data bracket j is equals to 0. Now x greater than n minus minus. Another for loop from j is equals to 0 to j less than 6 at j plus plus rate. X child ptr at j will be stored at null. Now np1 data at 0 position will be equals to mid np1 child ptr at np1 on n will be equals to x np1 child at np1 on n plus 1 will be equals to np3. np1 call n plus plus root is equals to np1 now else y is equals to x child ptr at I and mid is equals to y at data at 2 and y on data at 2 is equals to 0. Y will store n minus minus. Now for loop j is equals to 3, j less than 5, j plus plus, np3 data j minus 3 is equals to y data j np3 n plus plus y data bracket j is equals to 0, y n minus minus x child ptr at I plus 1 is equals to y x at child ptr I plus 1 is equals to np3 return Now we will write a function to insert into the tree. Void insert argument as int a so int I comma temp x is equals to root. If x equals to null, then root is equals to init and x will be equals to root. Otherwise, if x is a leaf and x at 9 repeat and x at n is equals to 5, and temp is equals to split child x comma minus 1 x is equals to root if a is greater than x at data at I and a is less than x at data I plus 1, I plus plus, and break. Else, if a is less than x at data 0, then break. Else, continue. X is equals to x at child at I. Else, while x leave is false, for loop I is equals to 0 when I is less than x at n. I plus plus. If a is greater than x at data I and a is less than x on data I plus 1, I plus plus, break. Else, if a is less than x data break. Else, continue. If x child at n is equals to 5, then temp is equals to split child at x comma I x data at xn on n is equals to temp x at n plus plus continue. Else x is equals to x child ptr I x on data at x at n is equals to a sort x at data x at n x at n plus plus. Now let's write a code for the main block. First we will declare some variables as int I, n and t. Now we will request enter number of element to be inserted. In at n. Now see out. Now we will enter the element. So enter the element now we will write a for loop. So I is equals to 0 to I less than n at I plus plus. So cn t and insert t. Now we will traverse this tree. So see out traversal of b plus tree. Traverse root. Let's execute this. We will enter 5 elements 2, 3, 5, 7, 9. As you can see, we have successfully traversed our first B plus tree. Let's get back to our slides.
Next, deletion. While deleting any element from B plus tree, we have to be careful not to break any properties of B plus tree. Like, all the leaves must be present at the same level or elements must be in ascending order. Now let's try these operations in a code editor.
Start by creating a B plus tree. First, we will declare a global variable int max equals to 3. Then we will create a class pptree and a class node boolean is leaf int start key comma size node star ptr and a friend class pptree. Now public node variable. Now we will write class pptree so node star root void insert kernel int node star comma node star. Void remove internal int comma node star comma node star. And a node function find parent node node star. Now public pptree the constructor a search function a insert function void remove void display star get root p is equals to new int bracket max r is equals to new node star bracket max plus 1. So BP tree equals to null. Now void B, BP tree insert int x if root is equals to null, then root is equals to new node. Root calls key at 0 stores at xx. The root checks its leaf size is equals to 1. Else node cursor is equals to root node star parent while cursor is leaf is equals to false. Parent equals to cursor now for loop int I is equals to 0 to I less than cursor size I plus plus. If x is less than cursor key at I cursor is equals to cursor at ptr at I. If I is equals to cursor size -1, cursor at ptr I +1 break. Now if cursor size is less than max, then int I is equals to 0 while x is greater than cursor key at I and then I is less than cursor size. I plus plus. For loop int is equals to cursor at size and j is greater than I, j minus minus. So cursor calls key at j is equals to cursor calls key at j minus 1. Cursor calls key at I is equals to x. Cursor calls size plus plus. Cursor calls ptr at cursor size is equals to cursor ptr at cursor size minus 1. Now cursor at ptr cursor size minus 1. Cursor ptr equals to null. Else node equals to new int virtual node max plus 1. For int I is equals to 0 to I less than max at the rate I plus plus. So virtual node at I is equals to cursor e at I int I is equals to 0 comma j while x is greater than virtual node bracket I is less than max I plus plus for int j is equals to max plus 1 comma j is greater than I j minus minus virtual node at j is equals to virtual node at j minus 1. So virtual node at I is equals to x So new leaf is leaf is equals to true. Cursor size is equals to max plus 1 by 2 new leaf size is equals to max plus 1 minus max plus 1 divided by 2. Cursor bracket cursor size is equals to new leaf. New leaf at new leaf size is equals to cursor ptr max. Now void bp tree insert internal int x comma node star cursor comma node star child. If cursor size is less than max, then int is equals to 0 while x is greater than cursor at key at I and I is less than cursor of size I plus plus. for loop int j is equals to cursor size j is greater than I j minus minus cursor at key at j is equals to cursor j minus 1. Now cursor key bracket I is equals to x cursor size plus plus cursor at ptr bracket I plus 1 is equals to child else node star new internal is equals to new node int virtual key is max plus 1 node star virtual key at max plus 1 star virtual ptr at for int I is equals to 0 I less than max I plus plus virtual key I is equals to cursor key for int I is equals to 0 I less than max plus 1 I plus plus virtual ptr I equals to cursor ptr at I. Node star pp tree find parent node star cursor comma node star child node star parent if cursor is leaf or cursor at ptr 0 is leaf. Then return null. For loop int I is equals to 0, I less than cursor size plus 1 I plus plus f cursor ptr equals to child parent is equals to cursor return parent else parent is equals to find parent cursor ptr child if parent not equals to null return return parent. Now void pp tree remove int x if root equals to null, then cout empty. Else node star cursor equals to root. Node star parent int left sibling comma right sibling. So while cursor is leaf equals to false, so for int I is equals to 0, I less than cursor size, and I plus plus parent is equals to cursor left sibling is equals to I minus 1, right sibling is equals to I plus 1. If x is less than cursor is at I, then cursor will be equals to cursor ptr. Now if I is equals to cursor size minus 1, equals to I, right sibling equals to y plus 2. Cursor is equals to cursor r bracket I plus 1 break bool found is equals to false. Suppose for pose equals to 0, pose is less than cursor size pose plus plus. If cursor key at pose is equals to x, then found equals to true and then break. Now if not found, then out not return. Now if cursor size equals to 0, then cout right delete cursor delete cursor ptr delete cursor root is equals to null. Return for loop int I is equals to cursor size equals to 0, j less than right node size I plus plus comma j plus plus cursor key at I is equals to right node cursor here add cursor size equals to null. Now see out merging two remove internal at right sibling minus 1 comma parent comma right node delete right node key right node right node. Now void tree display cursor if cursor is not equals to null or I equals to 1 I less than cursor size I plus plus see out cursor, cout cursor, key at I, cout handle, if cursor is leave not equals to true, and for int I equals to 0, I less than cursor size plus 1, I plus plus, okay, cursor ptr. Now node star bp tree get root. Return root. Now we will write the main block. We will start with an empty tree, bp tree, node. Now node dot insert 5, node dot insert 15, node dot insert 25, node dot insert 35, node dot insert 4, node dot display, node dot get root, node dot remove fifteen, node dot display, node dot get root. Let's execute this. As you can see, this program is working flawlessly. We have successfully deleted the key 15. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, B plus trees are fast at performing all its operations. Next, all the leaves must be present on the same level and data is only stored in the leaf node. Next, elements of the B plus tree are sorted in ascending order from the left to the right. Finally, every node contains one more pointer than the number of elements of the node.
Let's try to understand what is a bubble sort algorithm. The bubble sort algorithm is one of the fundamental and simplest forms of algorithm used to sort a collection of elements. The collection of elements can be either a set of numbers or characters. The control iterates through a sequence of numeric or character type elements in the bubble sort algorithm and rearranges them into ascending or descending order. The bubble sort algorithm rearranges one element at a time. The bubble sort algorithm is also known as the sinking algorithm. Here we have some random distributed elements which are 30, 10, 20, 50 and 40. And after performing the bubble sort algorithm, all the elements are sorted as 10, 20, 40 and 50. So how is it done? We will see in the next segment where we will understand the working terminologies of bubble sort algorithm. The bubble sort algorithm will not get implemented on the entire array in one go. Instead, it compares two adjacent pairs of elements in an array. If the elements are not in the correct order, then they are swapped, so the largest of the two moves towards the right. And this process continues until the most significant element, or bubble, is moved towards the highest position. After the first process is finished, the search for the next most significant object starts. And the swapping continues until the whole array is in correct order. This process is employed when you want to arrange the elements in ascending order. To understand the logic in a better way, let's go through an example. The example on my screen consists of 5 elements. According to the bubble sort algorithm logic, we need 4 iterations to sort all the elements in the ascending order or in descending order. The elements in the array are as follows. They are 3, 8, 4, 2 and 12. So in this array, the index begins with 0 and ends with 4. And each time, the bubble sort algorithm goes through the data element list and it is known as a pass. Let us analyze the total number of comparisons required to sort the array in the correct order. According to the formula, if n is the total number of elements in an array, then the total number of comparisons needed to sort the entire array can be calculated by a simple formula shown on my screen. That is, n is equals to n minus 1. So in this scenario, we need 5 minus 1, that is 4 comparisons or passes to sort the entire array. In the first pass, there are 4 steps. Let us select the first 2 elements, that is 3 and 8. According to the requirement, we need to sort this array in the ascending order. Hence, when we compare 3 and 8, clearly we get 3 as the least number, so we do not need to swap them. Next is the step 2. Comparing the second and third elements, which are 8 and 4. Here, we need to swap these 2 elements because 8 is always greater than 4 and it requires placing the elements in the ascending order. Now moving ahead, we have step 3. Moving on to the third and fourth elements, which are 8 and 2. And here again we need to swap 8 with 2 because 8 is greater than 2. And in the step 4, we have the last elements, which are 8 and 12. There is no need to swap because 8 is already less than 12, so you can see it clearly. So now we enter into pass 2, and in pass 2 we need 3 steps. So the first step, in the second pass, let us select the first 2 elements, which are 3 and 4. no swapping is necessary as they are already in order. Next we have step 2. In step 2, we need to select the elements 2 and 4. As you can see, 2 is always less than 4, so there is no swapping required. Next we have step 3. In step 3, we need to compare the elements 4 and 8. And here, we may not need any switching because 4 is already less than 8. Now here you can see that we are not comparing 8 and 12 because the last element is already sorted. Now, we have come to the last pass. And here, there is only one step. The step is to compare the first two elements, 2 and 3, and then swap them as 3 is greater than 2. Now, the array is finally sorted and we do not need to do any more comparisons. After understanding the working process of the bubble sort algorithm, we will see its pseudocode. In this pseudocode, there is a function named as bubble sort. The bubble sort function includes an array of collections of sortable elements. Let us consider n as the length of the array. After that, we have to repeat comparisons for the first element to the last element of the array. If the first element is greater than its next consecutive element, then we must swap both the elements and place them correctly. We do not need to switch after closing this repeated statement and getting out of the loop. This bubble sort function will end. After understanding the pseudocode of the bubble sort algorithm, let's learn about the optimized bubble sort algorithm. So we can optimize the algorithm's inner loop by programming it to avoid the comparison at n-1 position after every iteration, since the nth element is already sorted in the previous iteration. More generally, more than one element may be placed in their final position on a single pass. All the elements after the last swap are sorted in every pass and do not need to be rechecked. Optimized bubble sort algorithm allows skipping over many elements. This results in a worst case, that is 50% improvement in comparison count, and adds little complexity because of the new code subsums the swapped variable. Next, we will learn variations of the bubble sort algorithm. So, there are two variations of the bubble sort algorithm. They are odd even sort and cocktail shaker. So, odd even sort is a parallel version of bubble sort for the message passing system, whereas cocktail shaker is a sort of bidirectional bubble sort that first goes from beginning to the end and ends to the beginning. After knowing the variation of the bubble sort algorithm, now we will see the complexity of bubble sort algorithm. So the best case of the bubble sort algorithm is big O of n, where n is the number of elements being sorted, and worst and average cases of the bubble sort algorithm are big O of n into n, and lastly, the space complexity of the bubble sort algorithm is big of 1. Here, n is the number of data elements being sorted. Let us understand when this complexity occurs, the best case of bubble sort algorithm is O of n, which occurs at all the data elements in an array are already sorted. Here we have an example with some data elements in an array which are already sorted, that is 10, 20, 30, 40 and 50. Next, talking about the average and worst case. The worst case and average case of the bubble sort algorithm is O of n to the power 2, that is n squared or n into n. It occurs when all the data elements in an array are reversely sorted. Again, we have an example that consists of data elements that are reversely sorted, that are 50, 40, 30, 20 and 10 in an array. Lastly, we have space complexity. The space complexity of bubble sort algorithm is O of 1, because only one additional variable is required to implement bubble sort algorithm, that is temporary variable. We came to the last topic where we will understand 4 main applications of bubble sort algorithm. First application of bubble sort algorithm states that this sorting technique is used to sort the elements in a specific order. The bubble sort algorithm uses less storage and is the second application of bubble sort algorithm. Third, the real-life application states that the bubble sort algorithm is used to sort the students based on their height in a line. Lastly, bubble sort is used to create a stack, pile up the elements based on their height. After covering all the bubble sort algorithm topics, we will now see a practical demonstration of bubble sort algorithm. Now, on my screen, we have an example for bubble sort algorithm. So let us get started with the code. In this code, at the first position we have some header files, that is standard input, output, standard library, etc. After that, we will define the main function. In the main function, we will declare an array with maximum size of 50. So here, you can see that we have the first array variable that size is 50. Size will be defined with declaration only because we cannot change the array size in the runtime. After that, we will declare 4 variables, that is a, b, num and temp. Num variable will store the number of elements of an array. After that, we will ask the user how many elements are required for the array using printf function. So here is the printf function where we will be asking the user to enter the number of elements in an array. And the user will enter the elements, and this will be done using scanf function. Then finally, we will print all the elements that the user wants to store in an array using another printf function. We will have 3 loops. Firstly, there will be a loop from the first element to the last element of the array. So this is the first for loop we need. Then second, the for loop will use the variable a for the rotation purpose. As we know, rotation equal to number of elements minus 1. So it will make a loop from index 0 to number minus 1. The last loop is used for how many passes will be required for the implementation. And we already pass equally to the number of elements minus number of rotations minus 1. So there is the loop from index 0 to number minus a minus 1. Then there will be the if condition, stating that if the first element of an array at index b is greater than the element at the index b plus 1, then we will make swap. Then we will come out of the loop and we will print all the array elements after performing the bubble sort algorithm. Now let's quickly execute this program and see the output. So you can see the program got successfully executed. Now let us enter the number of elements. Let me choose 5. Now let us enter the elements in a random order. So this was the array input 3, 2, 4, 1 and 5. And here, after executing the bubble sort algorithm, we have the sorted array, that is 1, 2, 3, 4 and 5.
Let's get started with an introduction to insertion sort. Insertion sort is basically a sorting algorithm in which each item in the final sorted array is sorted one at a time. And it is significantly less efficient than more sophisticated algorithms like quicksort, heap sort, or merge sort on larger datasets. Now, let's discuss the algorithm of insertion sort. Let's say we have an array. We will start with traversing the array from index 1 to n-1. While traversing, we will compare elements at the current index to its predecessor. If the data at the current index is smaller than its predecessor, then we will compare it with the element before that. After that, we will shift bigger elements to an index up to make space for swapped elements. Then we will shift the bigger elements to an index up to make space for the swapped element, and then we will iterate the same steps again to sort the complete array. We have now introduced the insertion sort and its algorithm. Now let's implement this algorithm in the code editor. We will start with creating a function to sort an array using insertion sort. So void insertion sort we will give it argument as int array arr comma int size. We will declare variables int I comma key comma j. Now we will create a loop, for loop, from I is equals to 1 to I less than size I plus plus. Here we are traversing this array from index 1 to the size n minus 1. So key is equals to ARR at I and j is equals to I minus 1. Now we will move the elements of ARR 0 to I minus 1 that are greater than the key to one position ahead of the current position. So while j is greater than equals to 0 and ARR at j is greater than key, then we will swap these. So ARR at j plus 1 is equals to ARR at j and j will be equals to j minus 1. And then we will assign ARR j plus 1 is equals to key. Now we will write a function to print this array of size void print array. We will give its argument as int array and size. We will declare int I is equals to 0. For loop I is equals to 0, I less than size I plus plus, cout ARR ARR bracket I and cout handle. Now we will write the main block. So int ARR is equals to 12, 11, 15, 9, 6, 7. And size is equals to, we will find the size using size of. So size is equals to size of ARR divided by size of ARR at index 0. Now we will print this array without sorting. So cout unsorted array and we will print array ARR size. Now we will call insertion sort ARR size. Cout we will print this array sorted now we will again call print array argument as arr comma size. Now let's print this. As you can see, our function is working flawlessly. It has sorted this array.
Let's get started with an introduction to selection sort. The selection sort algorithm is an in-place comparison-based method that divides the list into two halves, with the sorted portion on the left and the unsorted half on the right. Then the smallest element from the unsorted array is chosen and swapped with the leftmost element, and that element is added to the sorted array. Now let's discuss the selection sort algorithm. Let's say we have an array. First, we will divide this array in two subarrays, unsorted array and sorted array. Then, we will divide the minimum element from the unsorted array and swap it with the leftmost element of this unsorted array. After that, we will add it to the unsorted array. We will keep repeating this process until there are no elements left on the unsorted array. We have now introduced selection sort and its algorithm. Now, let's implement this algorithm in the code editor.
We will start by creating a function swap. The argument will be integer pointer x, comma, integer pointer y. We will declare an element temp to store the value of pointer x. Then we will store pointer y's value in x. Then we will store temp's value in y. And that's how we can swap them. Next, we will write the definition of selection sort function. Void selection sort. Argument will be int array arr, comma, int n. We will declare variables int I, j, and a min underscore idx variable to store the minimum index. Now we will one by one move boundaries of unsorted subarrays. So for loop I is equals to 0, where I is less than n minus 1, I plus plus. We will find the minimum element in this unsorted array. So min underscore idx is equals to I. Now for j is equals to I plus 1, j less than n, j plus plus. If array element at jth location is less than array at the min index, then min idx will be updated with j. Now we will swap the found minimum element with the first element. So we will call swap function with argument as ampersand ARR at min idx, comma, ampersand ARR at ith location. Now we will write a function to print this array. So void print array argument as int ARR and its size int n. For loop int I is equals to 0, I less than n, I plus plus, cout ARR at I cout handle. Now we will write the code for the main block. So int ARR is equals to 4, 2, 1, 8, 3. We will find the size of this array. So int n is equals to size of array ARR divided by size of this array's first element. Now we will call selection sort function argument as ARR, n. Then we will try to print this. So cout sorted array and we will call the function print array to print this array ARR, n. Now let's try and execute this program. As you can see, we have successfully sorted this array using selection sort algorithm. Let's get back to our slides. Let's get started with what is a binary heap. It's a complete binary tree with all levels completely filled except the last level, where all leaves are to the left as far as possible. A binary heap can be either min heap or max heap. In a min binary heap, the elements at root must be minimum among all elements present in the binary heap. Max binary heap is like min heap, where root must be maximum among all elements. Now let's discuss implementation of heap sort. First, we will start with creating a max heap of elements present. Next up, we will remove the elements at the root and put it at the end of the array and put the smallest element at the root. After that, we will reduce the height by 1. Finally, we will heapify the root element again and repeat the process from step 2. Now let's try to implement this algorithm in the code editor. We will start by creating a function to heapify a subtree rooted with node I, which is an index in array ARR, and n is the size of the heap. So void heapify int ARR, comma, int n, comma, int I. Now we will initialize largest as root. So int largest is equals to I. Now we will define the left and the right subtree. So int L is equals to 2 into I plus 1 and int R is equals to 2 multiply with I plus 2. Now if the left child is larger than root, then if L is less than n and ARR at L ARR at L is greater than ARR at largest, so the largest will be equals to L. Now if right child is larger than the largest so far, so if R is less than n and ARR at R is greater than ARR at largest, so largest is equals to R. Now if largest is not root, so if largest is not equals to I, so we will swap ARR at I with ARR at largest. And then we will recursively call heapify for the affected subtree. ARR, n, largest. Now we will write the main function to do heap sort. So void heap sort int ARR bracket int n. Now we will start by building heap. So for int I is equals to n by 2 minus 1, where I is greater than equals to 0 at I minus minus. We will call heapify for ARR, n, I. Now we will one by one extract an element from the heap. So for int I is equals to n minus 1, where I is greater than 0 at I minus minus. Now we will move current root to end. So swap ARR at 0 to ARR at I. And we will call max heapify on the reduced heap. So heapify ARR, comma I, comma 0. Now we will write a function to print this array. So void print array int arr, comma int n. So for int I is equals to 0, I less than n, plus plus I, we will do cout arr bracket I is and a cout and L. Now let's write the code for the main block. So int arr is equals to e, comma 18, comma 12, comma 14, comma 5, comma 6, comma 2. Now we will write a statement to find the size of this array. So int n is equals to size of arr divided by size of the first element of the array, arr 0. Now we will call heap sort function. So heap sort for arr, comma n. Now let's print this array. So cout sorted array is print array at arr, comma n. Now let's try and execute this program. As you can see, our sorting function is working flawlessly. Now let's get back to our slides. Till now, we have discussed the binary heap and the algorithm of heap sort. Now let's discuss some applications of heap sort. First up, it can be used to sort a nearly sorted series of data. Next, it can be used to find minimum or maximum elements of the series with ease. Also, it can be used to solve problems which require some sort of priority.
Let's get started with what exactly is divide and conquer algorithm. A divide and conquer algorithm iteratively divides a problem into two or more subproblems of the same or relative type until they are simple enough to be solved directly. The subproblem solutions are then integrated to solve the original problem. There are three steps involved in the divide and conquer principle, that is, divide, conquer, and combine. The first step is to divide the significant problem into smaller subproblems. The second phase is to conquer the solutions to all divided subproblems. Then, the final step is to combine and merge all of the solutions to create a definite solution. We will understand this by an example right here on my screen. Suppose we have a large problem We can use divide and conquer technique to divide it into n number of subproblems such as problem 1, problem 2, problem 3, problem 4 and so on until we reach the problem n. Then we conquer all the solutions to the specified subproblems as solution 1, 2, 3, 4 and so on. And finally, we merge all the solutions to get one definitive solution. Now that was divide and conquer algorithm. Followed by that, let us get into merge sort algorithm. So merge sort is one of the most efficient sorting algorithms. It is based on divide and conquer strategy. Merge sort continuously divides a list into numerous sublists until each sublist contains only one entry, then merges all those sublists into a sorted list. There are 4 elements on my screen. We have 7 and 3 in the left half and 5 and 2 in the right half. After dividing the 4 elements in half, we combined all the items in ascending order, that is 2, 3, 5 and 7. In the next segment, we are going to understand how it happened and we are going to learn the working procedure of merge sort algorithm. There are 2 approaches to implement the merge sort algorithm. The first method is top-down approach and the second method is bottoms-up approach. The first method, that is the top-down approach, implies that it begins with the large picture. From then, it's broken into smaller chunks. Now the second method, that is the bottom-up technique, which starts with a specific number of jobs and works its way up to the general. Let's have a look at how to implement the merge sort algorithm using top-down approach. The top-down merge sort approach is the methodology that uses a recursion mechanism. It starts at the top and proceeds downwards, splitting the array into 2 halves, making a recursive call and merging the results until one gets to the bottom of the array. For a better understanding of the top-down approach method, consider the following scenario right here on my screen. We have an example of an array of size 6 consisting of elements 7, 3, 9, 5, 6 and 4, starting with 0 and ending with 5. Using the following formula, we'll divide the array by its middle. That is, middle is equals to left plus right divided by 2. We have 3 elements on the left and 3 elements on the right near the middle. So according to the top-down strategy, we divide the given array in half, resulting in 3 elements, that is 7, 3 and 9 on the left and 5, 6 and 4 on the right. Next, we sort all these elements in ascending order. By doing so, the first half will be 3, 7 and 9 and the right half will be 4, 5 and 6. And after merging all of them, we will have the sorted array, that is 3, 4, 5, 6 and 9. Next, we will understand the bottoms-up approach. An iterative process is used in bottoms-up merge sort approach. It starts with a single element array and then joins 2 neighboring items while also sorting them. The combined sorted arrays are combined and sorted again only until one single unit of the sorted array elements remains. Now let us look at an example right here on my screen. In the first iteration, we will merge pairs of array sizes by 1, sorting each of the 2 elements. When you iterate the array by size 1, the elements 7 and 3 become 3 and 7. Similarly, 9 and 5 become 5 and 9. And finally, 6 and 4 become 4 and 6. We will merge the pairs of array size by 2 in the next iteration with the bottoms-up method. As a result, the elements 3, 7 and 5 will become 3, 5 and 7. And the same way, 9, 4 and 6 will become 4, 6 and 9. In the last iteration, merge pairs of array size by 3 so that after sorting 3, 5, 7, 4, 6 and 9 becomes 3, 4, 5, 6 and 7 as sorted arrays. After understanding the working procedure of merge sort algorithm, we will now see the pseudocode of merge sort algorithm. We have a function called merge sort in this pseudocode, and parameter of the function contains an array named as array and 2 variables named as left and right. If the number of elements in the left is greater than the number of elements on the right, we will get a middle using formula left plus right divided by 2. The merge sort is called and this function now has an array a left variable and right variable. By calling merge sort, we have array left as middle plus 1 and right variable. And finally, by calling merge sort, we have left, middle and right variables. In our upcoming segment, we will implement the merge sort method in a practical demonstration. In the next section, we will discuss the complexity of merge sort algorithm. First, we will look into the time complexity of merge sort algorithm. As we all know, time complexity in data structures is divided into best case, average case and worst case. The best case of merge sort algorithm is big O of n into log n. Average case of merge sort algorithm is big O of n into log n. And the worst case of merge sort algorithm is big O of n into log n. The number of elements being sorted is given by n. Merge sort's time complexity is big O of n star log n in all three situations, that is worst, average and best, because it always divides the array into two halves and merges the two halves in linear time. It takes up the same amount of space as the unsorted array. As a result, it is not a good idea to use it to search big unsorted arrays. Moving on to the space complexity of the merge sort algorithm. The space complexity of the merge sort algorithm is large O of n. In the merge sort algorithm, we store the left and right parts of the merged array in the temporary arrays and then utilize the original array to keep the entire merged array. In the worst case scenario, the left and the right sub arrays will each be n by 2 in size, and then the total auxiliary space will be big O of n, resulting in a space complexity of big O of n. Following that, we will look into several applications of the merge sort algorithm. So the first application is merge sort is an efficient way to sort linked list in big O of n log n time. Subsequent application of the merge sort algorithm is for linked lists. Merge sort implemented without taking up more space. Followed by that, the merge sort method is used to count the number of inversions in a list. Last application states that in internal sorting, the merge sort is employed. Now let us look into some of the drawbacks of merge sort algorithm. So some of the drawbacks of merge sort algorithm are: for smaller assignments, merge sort algorithm is slower than the other sorting algorithms. For temporary array, the merge sort technique requires an additional memory space, that is, space of big O of n. Now, let us look into a practical demonstration of merge sort algorithm.
On my screen, we have an example for merge sort algorithm. To define constants or micro substitution, we use the hash define as preprocessor directive with a constant variable max of 10. Following that, two arrays, array 1 and array 2 are declared. We declare array 1 and initialize it with elements like 8, 4, 7, 6, 2, 3, 5, 9, 10, 4 and 1. Array 2 is used for temporary array. Then, to implement the merge sort concept, we declare a merge sort function. We specify three variables in this function parameter, that is left, right and middle. The left variable is used to display the left part of the array 1, the right variable is used to display the right part of the array 1, and middle variable is used to indicate the middle or center of the array in this function. We utilize the for loop in this function, setting the left to level 1, the middle plus 1 to level 2, and the left to variable I with the condition that level 2 is less than or equal to the middle and level 2 should be less than or equal to the right of the array. We have a condition in this for loop that if level 1 of array 1 is less than or equal to level 2 of array 1, we will initialize all the consecutive elements of level 1 of array 1 to array 2. Else, we will initialize all the successive elements of level 2 of array 1 to array 2. Out of for loop, all subsequent elements of level 1 of array 1 will be initialized to array 2 until level 1 is less than or equal to the middle. All successive elements of level 2 of array 1 will be initialized to array 2 until level 2 is less than or equal to the right of the array. Using the loop, which will run from I equal to the left of I is less than or equal to right, we initialize all the items of array 2 to array 1. We have declared one more function in this code, namely sorting. Out of the merging sort function, in which only the left and right variables are defined, we specified the middle function in the sorting function with the condition that if the left is less than the right, the middle will be calculated as left plus right divided by 2. Then we called a sorting function passing left as middle as right, and then another sorting function passing left as middle plus 1 and right. Finally, we use the merge sort function passing left, middle and right to the sorting array 1, otherwise we would return nothing. We entered the main function out of the sorting function where we declared the counter variable I and printed the array before sorting using the printf function in for loop, where I will run from index 0 to the array's maximum size. After that, we invoked sorting method passing left as 0 index number and right as the array's maximum value. Finally, after doing the merge sort process, we will print the array using the printf function and for loop. We will run from 0 to the array's maximum value. Then we compile the program and run it. Now let's try to quickly execute this program and see the output. So there you go, the program got successfully executed and the list before sorting is 8, 7, 6, 2, 3, 5, 9, 10, 4 and 1. And the list after sorting is 1, 2, 3, 4, 4, 5, 6, 7, 8, 9 and 10.
Let's get started with an introduction to quicksort. A quicksort is a highly efficient sorting algorithm and it is based on partitioning an array into smaller subarrays. And then we will sort these two resulting subarrays in the same manner. This algorithm is quite efficient for large size data sets as its average and worst case complexities are big O of n square. Now let's discuss algorithm of quicksort. Let's say we have an array. First, we have to select a pivot. We can select either the first element or the last or medium or any random element as pivots. This pivot will dissect the array into two subarrays. Then we will shift all smaller elements than the pivot element to the left. Then we will again apply the same operation for the left subarray and take pivot like we did for the main array. We will perform the same for the right subarray as well. We have now introduced the quicksort and its algorithm. Now let's implement this algorithm in the code editor. We will start by creating a function swap. So void swap int star x comma int star y int temp is equals to star x is equals to star y is equals to temp. Now we will write a function which will partition this array. This function will take the last element as pivot and the pivot element at its correct position in sorted array and places all smaller elements to the left of the pivot and all greater elements to the right of the pivot. So int partition int arr comma int low comma int high. So int pivot equals to arr high now int I is equals to low minus 1. So for int j is equals to low, j less than equals to high minus 1. A plus plus. Now if current element is smaller than the pivot, so if ARR at J is less than pivot, then we will increment the I. Then we will swap ampersand array at I comma ampersand array at J. Then we will swap ampersand array at I plus 1 comma ampersand array at high. And then we will return I plus 1. Now we will write the main function that implements quicksort. So void quicksort int arr bracket comma int low comma int high. So if low is less than high, int pi is equals to partition arr comma low comma high. Now we will separately sort elements before partition and after partition. So quicksort arr comma low comma pi minus 1 and quicksort arr comma pi plus 1 comma high. Now we will write a function to print this array. So void print array int arr comma int size int high. So for loop I is equals to 0, I less than size, I plus plus, cout array at I cout handle. Now we will write the main block. So int array and comma 7 comma 8 Now we will find the size. So int n is equals to size of array is divided by size of array element at 0. Now we will call quicksort for array comma 0 comma n minus 1. Now we will print this. So cout sorted array now print array arr comma n. Now let's execute this. As you can see, we have successfully sorted our array.
In this session, we will be discussing the bucket sort algorithm in data structures. So the bucket sort algorithm divides the unsorted array into several groups known as buckets. So each bucket is sorted using any suitable sorting algorithm or recursively applying the same bucket sort algorithm. I know it's a little complicated to understand, so let's go through an example. So on my screen, we have an example of an array consisting of numerical elements, that is 12, 6, 37, 29, 11, 35, 21, and 22. Now, we will create some buckets with different ranges. So here we have different buckets ranging from 0 to 7, 8 to 15, 16 to 23, 24 to 31, and finally the last bucket with range 32 to 39. So 6 will be stored in the first bucket, followed by that 11 and 12 will be stored in the second bucket, followed by that we have 21 and 22 stored in the third bucket, followed by that we have 29 in the fourth bucket, and finally the last two elements, which are 37 and 35, stored in the last bucket. In the next stage, all the elements are sorted according to an order that might be ascending or descending. In our case, we have the ascending order. So the final result will be 6, 11, 12, 21, 22, 29, 35, and 37. So this is how the bucket sort algorithm works in real time. Now, the next topic, that is working off a bucket sort algorithm in a detailed way. So now we know the briefing of a bucket sort algorithm. Now let's learn the working of bucket sort algorithm in depth. Suppose we have an array consisting of decimal values or floating values as the input. So the first element is 0.47. Next we have 0.39, 0.23, 0.55, 0.29, 0.41, 0.59, and finally 0.31. Then we will create an array of size 10 and store 0 in each block. And each block of an array is used as a bucket for sorting the elements. Next we have step 2. Insert the elements into buckets from the array, and all elements are inserted as per the range of the bucket. Buckets ranging from 0 to 1, 1 to 2, 2 to 3, up to n minus 1 to n. Here, n is the number of elements in an array. So, for our example, 0.23 will be multiplied by 10, which is the size of an array, and that gives us 2.3, approximately equal to 2. So finally, we will insert 0.23 into the bucket number 2. In exact, we will insert other elements into other respective buckets. Followed by that, we have step 3. Elements of each bucket are sorted using the stable sorting algorithms. And finally, the step 4. In step 4, all the sorted elements of each bucket will be gathered and represented in the form of an array. As pseudocode is an informal programming description that does not require any strict programming language syntax, similarly, we will understand it effortlessly. So, in the pseudocode, first we will create n empty buckets. Next, we will insert all the array elements into buckets by multiplying the size of an array. We have to keep doing this for every array element as we understood this in working of the bucket sort algorithm. After that, we have to sort individual buckets using insertion sort. And finally, we will concatenate all the sorted buckets. Next, we will learn about the complexities of bucket sort algorithm. First, we will see about time complexity. So talking about the time complexity, we usually have three cases to summarize the time complexity. So first we have the best case. So that the best case is O of n plus k. Next we have the average case, that is O of n into n. And finally we have the worst case, that is O of n. Here n is the total number of elements to be sorted and k is the number of buckets. So let us understand all the three cases one by one. So first we have the best case. So the best case occurs when all the elements are uniformly distributed in the bucket with an equal number of elements in each bucket. If insertion sort is used to sort the bucket sort algorithm, then overall time complexity is O of n plus k. O of n complexity is for making the buckets and O of k complexity is for sorting all the elements. After understanding the best case, now we will see how the worst case occurs in the bucket sort algorithm. The worst case occurs when there are elements of close range in the array. They are likely to be placed in the same bucket. It makes the complexity depend on the sorting algorithm used to sort the elements of the buckets. Complexity becomes worse when all the elements are in reverse order, and if insertion sort is used for sorting, then time complexity becomes O of n into n. And lastly, we will learn how the average case occurs in a bucket sort algorithm. The average case occurs when the elements are randomly distributed in the array. It occurs even when the elements are distributed in uniform way. Bucket sorts run at the linear time. The average case holds true until the sum of bucket sort sizes is linear and in the total number of elements. Next, we will see about the space complexity. So the space complexity of all the bucket sort algorithms is O of n plus k. Lastly, we have stability. So talking about stability, so yes, the bucket sort algorithm is stable. After understanding the complexity of bucket sort algorithm, now we will compare the bucket sort algorithm with other algorithms. So first, we will compare the counting sort algorithm. Bucket sort can be worked as a generalization of counting sort algorithm. And if each bucket has size 1, then the bucket sort degenerates to counting 0. The variable size of bucket sort algorithm allows it to use O of n memory instead of O of m memory, where m stands for the distinct value that gives counting sort O of n plus 1 worst case behavior. Next, we will compare the bucket sort algorithm with quicksort. Bucket sort with two buckets is a practical version of the quicksort, where the pivot value always selects the median value of the value range. Another meaning of choosing the pivot in quicksort, such as a randomly selected pivot, makes it more resistant to clustering it in the input distribution. After that, we have the merge sort. The n-way merge sort algorithm starts by distributing the list into n sublists and sorting each one. Then, the sublists created by merge sort have overlapping ranges and cannot be recombined by a simple concatenation bucket sort. Lastly, we have one more sorting algorithm, that is radix sort for comparison. Top-down radix sort can be a particular case of bucket sort where both range of values and the number of buckets has contained the power of 2. This approach can accelerate the scatter phase since we only need to examine each element's prefix of bit representation to determine a bucket. At last, we have one more topic to learn, that is the applications of bucket sort algorithm. The bucket sort algorithm consists of two main applications. First, by using bucket sort algorithm, input is uniformly distributed on the range. And second, by using bucket sort algorithm, there are floating point values. Now let us go through a practical demonstration of bucket sort algorithm. Now on my screen we have an example for bucket sort algorithm. So we will begin with the header files, followed by that we will define a function, namely bucket sort algo. This particular function is to implement a bucket sort algorithm. In the function's argument, there will be an array, namely arr, and a variable num, which will store the number of elements in an array. After that, we will define two counter variables, which are I and j, and declare one more array, namely array1, with the same size of an arr array. So this particular second array will be used for displaying all the elements in the array1. We will have a for loop which will run from index 0 to the entire size of an array, and for this array, we will use the variable I as the counter variable. We will have another for loop to print all the repeated numbers with frequency in an array. We will run another for loop from index 0 to the last element of both the arrays, and elements of array and array1 will assign to arr array. Now we will exit from both the loops, and now we will enter into the main function where we will declare an array, namely array, with the size of 100 and two variables which are num and I. Next, we will ask the user to enter several elements of an array using printf function, and now the user will enter number of elements and we will scan that using the scanf function. Now we will ask the user to enter the elements of an array using printf function, and the entered elements will be scanned using the scanf function. And next we will print a before sorting and an array after sorting using for loops by calling the bucket sort algo function, and in this function we will pass the name of an array, that is an array, and the size of an array, that is num. Now let us try to execute this program and see the output. So there you go, the program got successfully executed. Now let us try to enter the number of elements, that is 5. Now let us enter all the 5 elements, 2, 3, 1, 4, and 5. So the array before sorting was 2, 3, 1, and 4, 5. Then the array got sorted using bucket sort algorithm, and the resultant array is 1, 2, 3, 4, and 5 in ascending order.
In this session, we will discuss the counting sort algorithm. So without any further ado, let's get started with an introduction to counting sort. A counting sort is a sorting algorithm that sorts the elements of an array by counting the number of occurrence of each unique element in the array. The count is stored in an auxiliary array, and the sorting is done by mapping the count as an index of that auxiliary array. Now let's discuss the counting sort algorithm. Let's say we have an array. First, we will find the largest element in this array to evaluate the range of the elements. Then we will create a count array to store the count of element from the array. Then we will update the count array's element with a cumulative count. At last, we will output each element from the array followed by decreasing its count by 1. We have now introduced the counting sort and its algorithm. Now let's try to implement this algorithm in the code editor. Let's start by creating a count sort function. Void count sort, its argument as int arr, comma int n. We will declare an array output with size 10 and an array count again with the size 10 and an integer variable max is equals to arr at 0. Now we will write a for loop to find the largest element of this array. So for int I is equals to 1, I less than n, I plus plus, if ARR at I is greater than max, then max will be equals to ARR at I. Now we will initialize the count array with all zeros. So for int I is equals to 0 to I less than equals to max plus I, count at I is equals to 0. Now we will store the count of each element in this array. So for loop int I is equals to 0, I less than n, I plus plus, count at ARR bracket I is plus plus. Now we will write a for loop to store the cumulative count of each array. So for int I is equals to 1, where I is less than equals to max, at I plus plus, count at I is equals to plus equals to count at I minus 1. Now we will find the index of each element of the original array in count array and place the elements in the output array. So for int I is equals to n minus 1, I greater than equals to 0, I minus minus. So output a count at ARR I minus 1 is equals to ARR at I, and then we will decrease count ARR I by 1. Now let's write a function to print this array. So void print array, so int ARR bracket comma int n. So for loop int I is equals to 0, I less than n, I plus plus, cout ARR at I, out and L. Now let's write the main block int ARR is equals to, we will write the element Now let's find out the size of this array. So int n is equals to size of array divided by size of array's first element. Now we will call the count sort function. ARR comma n. Now we will print this array. So print array ARR, comma N. Now let's try and execute this. As you can see, we have successfully sorted this array using counting sort. Let's get started with an introduction to radix sort. Radix sort is a non-comparative sorting algorithm. It avoids comparison by creating and distributing elements into buckets according to their radix. And for elements with more than one significant digit, this bucketing process is repeated for each digit while preserving the ordering of the prior step until all digits have been considered. Now let's discuss radix sort algorithm. Let's say we have an array. First, we will find the largest element in the array to decide maximum number of significant digits we will need to compare to sort this array. We will go through each significant place and sort the array one by one. First, we will sort the array according to the units place. Then we will sort according to the tens place. And then we will sort according to hundreds place and so on till the array is sorted. We have now introduced the radix sort and its algorithm. Now let's implement this algorithm in the code editor. We will start with an utility function to get maximum value in this array. So int get max with an argument as array arr, comma size n. We will declare variable int mx is equals to arr at 0, and we will write a for loop where int I is equals to 1 to I less than n at I plus plus if arr at I is greater than mx, then mx will be equals to arr at I, and then we will return the value of mx. Now we will write a function to do counting sort of array arr according to the digits represented by exponent. So void count sort at int arr, comma int n, comma int exp. We will declare an integer array output int I, comma a count array of size 10 where all elements are 0. Now we will store the count of all the elements of the array arr. So for loop I is equals to 0 from I less than n to I plus plus count arr at I divided by exp modulus of 10 plus plus. Now we will change count I so that count I now contain actual position of this digit in output. So for I is equals to 1, I less than 10, I plus plus, count I plus equals to count I minus 1. Now we will build the output array. So for loop at I is equals to n minus 1 to I greater than equals to 0, and I minus minus output count ARR at I divided by exp modulus 10 minus 1 is equals to ARR at I. And now count ARR at I divided by exp modular 10 minus minus. Now we will copy the output array of ARR so that ARR now contains sorted numbers according to the current digit. So for I is equals to 0, I less than n, I plus plus, ARR at I is equals to output at I. Now let's write the main function that will sort the ARR using radix sort. So void radix sort int ARR comma int n. Int m is equals to get max ARR comma n. Now we will do the counting sort for every digit. Note that instead of passing digit number, exp is passed. Exp is basically 10 raised to the power I, where I is current digit number. So for int exp is equals to 1 and m divided by exp is greater than 0, while exp is multiplied equals to 10, we will do count sort on ARR of size n with exp. Now let's write a function to print this array. So void print array int ARR comma int n for int I is equals to 0, I less than n, I plus plus, out array at I. Now let's write the main function. We will declare int ARR bracket with values 170, 45, 75, 90, 802, 24, 2, 66. Now we will find out the size of this array ARR. N is equals to size of ARR divided by size of ARR first element. Now we will call the radix sort function. And we will print this array. Now let's try and execute this. As you can see, we have successfully sorted this array using radix sort. Let's get back to our slides. At last, let's sum up what we have learned from this session. First up, radix sort can be used on lexicographically sortable data. Next up, radix sort utilizes the count sort algorithm. Next, radix sort is done by sorting elements using significant digits. Finally, radix sort consumes more memory space than quicksort.
So what exactly is a graph? So a graph is a data structure like any other data structure, example linked list, arrays, etc. So graph is a little different from the other types of data structures such as linked list and arrays. They are linear data structures, whereas graph is a non-linear data structure that consists of finite sets of vertices and a bunch of edges connecting with them. So what are these vertices and edges? So let us understand that a graph is usually represented by a set of vertices and edges. So a vertex is the node present in a graph. Imagine that you are a group of 5 friends. So each one of you is considered as a vertex and the network connecting you guys is known as an edge. So the overall graph of you people can be considered as G, and it is represented by vertices and edges set, where vertices is you and the network connecting you guys is called as an edge. So here you can see it clearly. Each one of the friend is called as a vertex and the network connecting them is called as an edge. And the entire graph is represented using a set of vertices and edges. Now moving ahead, we will understand the graph terminologies. Now at first we have the adjacency vertices and adjacency edges. So what are adjacent vertices? if there is an edge between two vertices, that is, one vertex or one node is connected to another node directly using just one single edge, then those vertices are called as adjacent vertices. Now, what are adjacent edges? If there is one common vertex between two edges, then those two edges are called as adjacent edges. Let's imagine this way. Let us imagine that we have three vertices and these three vertices are connected using two edges. So here we have one vertex which is common between these two edges. So such type of edges are called as adjacent edges. Next we have the degree. In an undirected graph, number of vertices adjacent to the vertex is called as a degree. Next is the path. The path is considered as a sequence of distinct vertices such that two consecutive vertices are adjacent to each other. Up next we have the cycle. A path that has only one repeated vertices are called as first and last vertices. Followed by that we have the walk. The term walk is self-explanatory. A walk is the sequence of vertices and edges in the graph which is used to traverse through one vertex to another vertex. Now we have entered the next segment of this particular tutorial where we will be discussing the different types of graphs available. So at first we have the finite graph. So what exactly is a finite graph? A graph is said to be finite when the number of vertices and the number of edges are in a finite number or in a countable number. Now the next type of graph is the infinite graph. So what exactly is the infinite graph? So the infinite graph is a typical opposite of the finite graph. So this particular graph will not have countable number of edges and countable number of vertices. The image here is an example for a typical infinite graph. Now followed by the infinite graph, we have the trivial graph. So what is a trivial graph? A graph is said to be trivial if there is only one single vertex without any edges. So this particular type of graph will only have vertex, that is only one single vertex, not more than one, and there will be no edge. If you have just one vertex, then there is no possibility of having an edge, unless if you have one single loop type of edge, which is connecting to itself. But in a trivial graph, we don't even have that. We just have one single vertex. So followed by trivial graph, we have a simple graph. So what exactly is a simple graph? A graph is said to be simple if there is only one and one edge between each vertex. So this particular example can be considered as a simple graph. So here, each and every set of vertices have one single edge between them. Now followed by the simple graph, we have the multigraph. So if there are multiple edges between the pair of vertices, then this particular type of graph is known as a multigraph. So here you can see that we have two vertices, A and B, and we have two edges connecting them. Not one, but two. But in a simple graph, we were supposed to have just one edge connecting the vertices. So this is the difference between simple graph and a multigraph. So followed by multigraph, we have a null graph. So what is a null graph? A graph is said to be null if there are only vertices and no edges between them. So remember the trivial graph, right? We just had one single vertex but no edges. But here we do have multiple vertices but no edges connecting them. So this type of a graph is considered as null graph. So followed by null graph, we have the complete graph. So what is a complete graph? A graph is called as a complete graph where each vertex must be connected with the other vertices using the edges. So the meaning of this particular type of graph is all the edges are connected to all the other edges using at least one single edge. So here you can see A is connected to B, D and C all together with at least one edge, and similarly all other vertices are connected to each other with at least one single edge. Now followed by the complete graph, we have the pseudo graph. So what is a pseudo graph? A pseudo graph is a graph where at least one vertex will have self-looping type of edge. So remember the self-loop or self-edge we have discussed in the trivial graph type. So this particular type of an edge where it connects to itself is called as a loop or kind of self-connecting edge. So any graph that has this kind of a edge is called as a pseudograph. So followed by the pseudograph, we have the directed graph. So what is a directed graph? Any graph is called as a directed graph where each edge has a direction associated with it. So far we have just discussed the edges which are connecting to one or the other vertex, but there was no direction. But here you can see that this particular edge has a direction, that is from B to A, not from A to B, it is from B to A. This type of edges which are directing the traversal of the graph are known as the directed graphs. Now followed by the directed graphs, we have the regular graph. So a graph is a regular graph where each vertex of the graph has the same degree. Now here you can see all the vertices have the same amount of degree, that is the connection between all the other vertices. So the degree of A is 3, so the degree of B is also 3, and the degree of D is C, and similarly the degree of C is also 3. So what I mean to say is all of these vertices have the same degree, that is 3. Now we have the weighted graph. So what is a weighted graph? A weighted graph is where each edge holds some weight that denotes the traversal cost through those edges. Now here you can see that all the edges have a different weight. The edge from A to B has the weight 5, and the edge from A to C has the weight 9, and the edge from C to B has 2, and the edge A to D as 8, and finally C to D as 7. So all these values are the weight or the cost to traverse from A to another vertex. So from A to B we have the cost 5, and A to C we have the cost 9, and similarly C to D we have 7, and so on. Now followed by the weighted graph, we have the connected graph. So what exactly is a connected graph? A graph is said to be connected where each pair in the graph is connected. Followed by a connected graph, we have the disconnected graph. So it is a typical opposite of the connected graph. A graph is said to be disconnected where each pair in the graph is not connected to each other. Now next we have the cyclic graph. So a graph is said to be cyclic if it contains at least one cycle in a graph, that is one complete traversal connection. So A can be traversed again from traveling A to C, C to D, D to B, and B to A again. So this type of a graph is called as a cyclic graph. Now next we have the acyclic graph. So it is the typical opposite of the cyclic graph. So here you cannot traverse to A again by traversing from A to C, C to D, and there is no connection between D to B. So the complete cycle is not available here. This type of graphs are called as acyclic graphs. So moving ahead, we have the graph representation. So generally, there are two different ways to represent the graph data structure. They are using adjacency matrix and adjacency list. So what is adjacency matrix? So adjacency matrix is a sequential representation. Adjacency matrix is used to represent which nodes are connected to which node. If there is an edge between two vertices, then the value of the corresponding element of the graph is 1, otherwise 0. If there is any weighted graph besides, then zeros and ones, we can store the weight of the edge as that particular number. Suppose that there is a connection between A and B, and it is represented as a weight of 5. Then there is a connection, so we will use the connection as true, but we will not represent it as 1. Instead, we will use the weight, that is 5, to represent it as 5, not as 1. If there is no weight, then we will represent it as 1, and if there is no connection, then we will represent it as 0. Now, undirected graph representation. So here you can see how we have represented a graph. So there is no connection between A to A, that is there is no loop, so the value will be 0. If there was a loop and if it was represented with a weight, then we could have written a weight here. Since we do not have weight, then the no connection is represented as 0 and a connection is represented as 1. We have a connection from A to B, so we have represented it as 1, and similarly to A to C, so and so on. Now, directed graph representation. So the simple difference between the directed and undirected graph representation is we did not have a direction in the previous segment, but here we do have directions. So B is connected to A, but A is not connected to B. So we will write it as 0 because the control is traversing from B to A, but not from A to B. So we need to take care of the traversal of control. So we are representing as 0, and you can see from D to B, we have one connection and the traversal is in the direction of D to B. So we will have 1 there. So here we have D and B, so we have 1. So in that way, we represent the directed graphs. Next, undirected weight graphs. So this was what we discussed before. Instead of zeros and ones, we will represent the weight here. So we do not have a connection between A to A, so that is 0 as usual, but we do have a connection from A to B, so we have represented it with a number that happens to be the weight of the edge. And remember, we do not have the direction here. This is undirected weighted graph. Now, if it were the directed weighted graph, then we could have seen the direction and represented the number with the weight. Now, after this, let us look into the adjacency list. So what is adjacency list? Adjacency list is a linked representation. In this representation, we maintain the list of its neighbors for each vertex in the graph. Every vertex of the graph contains the list of adjacency vertices. Array of vertices which have vertices indexed by each vertex number for every vertex. The array element points to the linked list of the neighbors of the vertex. So this might be a little complicated to understand, so let us understand this using an example. So directed graph representation implemented using linked list. So this is the directed graph we are using. So you can see that A is not connected to anything, so we have ended the address of next location as X, but B is connected to A and C is connected to A. Similarly, D is also connected to A. So that is how we represent the directed graphs using linked list. Next, we have directed graph representation using array. So A is not connected to anything, so we have represented as 0, and B is connected to B as well as A, so we have 1 there, and C is connected to B, so C is also connected to A, so we have 2 there. D is connected to A, C and B, so we have 3 there. Now we have the graph traversal. So graph traversal refers to the process of examining each edge and vertex in a graph. Graph traversing can be performed in 2 ways. The first one is breadth first search or BFS algorithm. BFS starts traversing the graph from root node and explores all the neighboring nodes. Then it selects the nearest node and explores all the new nodes. Queue data structure can be used in BFS algorithm. So the following image depicts the BFS algorithm working. It chooses the nearest node first, then it traverses to all the other nodes. So followed by BFS algorithm, we have the DFS algorithm, that is the depth first search algorithm. DFS starts traversing a graph from the initial node of the graph and then it goes deeper and deeper until it finds the node has no child. Then backtrack from the dead end towards the recently explored nodes. Stack is used for BFS algorithms. So this particular GIF image can be considered as the graph traversal which is performed using DFS algorithms. So if you don't know much about DFS and BFS algorithms, don't worry about that. Those particular tutorial videos are added in the description box below. You can go through it and understand BFS and DFS algorithms in a much better way. Now we will go through some of the applications of graphs. So some of the major applications of graphs are used in the websites, Google Maps, and social media websites like Facebook, and some security systems, and also software programming.
The Kruskal's algorithm is used to find the minimum spanning tree for a given graph. But what exactly is a minimum spanning tree or MST? Well, a minimum spanning tree is a subset of graph G having the same number of vertices as of graph G and edges equivalent to number of vertices minus 1. Along with these properties, it also has a minimum cost for the summation of all edge weights included in a minimum spanning tree. If you want to learn more about spanning trees, then please consider watching our video, which you can find in the I button section right away. Now coming back to the Kruskal's algorithm, the Kruskal's algorithm sorts all edges in increasing order of their edge weights and keeps adding nodes to the tree only if the given edge does not form a cycle. Also, it picks the edge with minimum cost at first and the edge with maximum cost at last. Hence, we can say that the Kruskal's algorithm makes a locally optimal choice, intending to find global optimal solution. That is why it is also considered as greedy algorithm. The data structure that we are going to use for implementing this Kruskal's algorithm is union find. But now you must be thinking, what exactly is this union find data structure and how it works? Well, union find is a data structure that keeps tracks of elements that are split into one or more than one disjoint sets, where a disjoint set is collection of two distinct groups or clusters that do not have single common element. The union find features two important operations named as find and union. The operation find returns the set or group to which provided element belongs. Basically, it constructs a bijection between the object provided and its set, whereas the union function joins two distinct disjoint sets to create a single subset. Let's understand how this data structure works with the help of real-life example. Let's say we have some singing magnets placed on table with a higher magnetic affinity towards each other. All these singing magnets present on the table are color coded with sky blue color. Now, due to the high magnetic attraction, the magnets A to E will form a strong magnetic field which will cause the bonding or connection of all these magnets. As a result, all these magnets will be grouped together. We will now color code this set with red color. Along with that, we'll also call this set as red. After that, the magnet F to I are also closer to each other. Thus, they will also form a connection. We'll call this set as green. Finally, this last set of magnets will also formulate a connection with each element inside a group. We will call this group as set purple. All these distinct magnets got distributed into three different disjoint sets. But as the magnetic attraction between these groups increases significantly, hence all these clusters of magnets will end up connecting with each other. This scenario can be related to the union function. Union function merges different sets into a single subset where the find operation helps in extracting the group of element to which the particular element belongs. Similarly, in this scenario, a particular magnet can be traced back to its group with the help of color code that we have maintained alongside the magnets. The use of union find in Kruskal's algorithm can be related to this example. While implementing Kruskal's algorithm, we are going to maintain three distinct disjoint sets. The first set will store edge weight values for all edges in a graph, whereas the second set will store tree hierarchy for a different nodes. The last set will store the ranks for all nodes included in an MST. By using the union find structure and its operation, we can justify the entry of each edge into the spanning tree, which we will explain in the implementation of this algorithm. But let's understand the functioning of this algorithm primarily. The Kruskal's algorithm begins with sorting all edges into increasing order of their edge weights. This sorting is done to include edges with the least edge weight primarily into the tree structure. After that, we'll pick the first smallest edge and we'll check if it generates any cycle in the tree structure or not. If it does not form any cycle, then we will include that edge into our spanning tree. Otherwise, we will discard it. We will keep repeating this process until mod of v-1 edges are included into our MST, where v is number of vertices. Now moving ahead, let's discuss how we can create a minimum spanning tree using Kruskal's algorithm. This given graph GVE contains 12 edges and 6 vertices, and we are supposed to find out G dash such that the number of vertices is equal to 6 and the number of edges is equal to v minus 1, that is 6 minus 1, which is equal to 5. The one more condition that the formulated structure must abide by is that the summation of all included edge weights must be the minimum possibility for this spanning tree. Going forward, we'll discuss how we are going to create MST for this graph using Kruskal's algorithm. The first step that we need to perform is removing all the loops or parallel edges from our graph. Hence, primarily, we'll remove these two present loops. The next step that we are going to perform is arranging all the edges in increasing order of their weights. The reason behind maintaining the sorted list is to make sure that the first edge for insertion is of a minimum cost. Here, I have maintained the sorted list for all the edges that are part of our graph. So according to this sorted list, the first edge that we are going to insert in our MST is edge EF, as it has minimum weight cost, that is 2. The next edge that we have in our sorted list is edge FD. It also has an edge weight equal to 2. Hence, we'll include it in our spanning tree. The third edge in our sorted list is edge BC with weight 3. The inclusion of this edge does not formulate any circle in our tree structure, hence we'll add it to our MST. The next edge is edge CF, having a edge weight 3. So we'll include it in our MST structure. The fifth edge that we are going to pick is edge CD, having weight 4. But the inclusion of this edge inside our spanning tree will create a loop, and the structure that contains a loop can never be considered as tree. Hence, we have to exclude this edge. The next edge is edge BF, and the inclusion of this edge will also generate a cycle in our spanning tree structure. So we will exclude this edge as well. The next edge is edge BD. This edge has weight value 6. The inclusion of this edge can also create a loop in our structure, so we'll have to discard this edge as well. The next up is edge AB with a weight value 7. Even though this edge has higher weight value than previous edges, but it does not formulate any cycle in our MST, so we'll include it in our tree structure. By doing that, we have generated v-1 edges for our spanning tree. Thus, we won't iterate further in our sorted list. This generated MST has minimum possible cost for our graph GVE, which is 17. I hope that you guys have understood the MST implementation process using Kruskal's algorithm. Cause in the next slide, I have a problem for all of you guys to assess your understanding of Kruskal's algorithm. The graph shown on your screen contains 10 vertices and 18 edges. And for this graph, you are supposed to generate a minimum spanning tree such that it contains 10 vertices, 9 edges, and minimum construction cost. In order to do that, you can take out your pen and paper to draw the spanning tree structures based on the step that we have discussed till the time. I'm aware that this graph is quite strangely structured. However, if you can solve this problem, you will undoubtedly be able to solve other difficult problems out there. And of course, if you are confused about any step, then you can reiterate through the session. But here I am going to give you guys a little moment to figure out your answers. Well, now that you guys must be ready with your solution, so let's check if it is true. The highlighted part of this graph is possible structure for a spanning tree with minimal cost. By removing other edges, the MST will look something like this. I hope you guys have got the right answer. On that note, let's dive further and discuss the implementation strategy for Kruskal's algorithm. While implementing the Kruskal's algorithm, primarily we'll generate a C structure for keeping track of the source and destination node along with its weight. After that, we'll sort all that edges of a graph in increasing order of their edge weights. Moving ahead, we'll create three distinct sets to maintain nodes of a graph, their hierarchy in tree, and corresponding ranks for every node. For each insertion of an edge in MST, we'll update the rank and parent of each node. If the two nodes have the same parent node, then we will not insert the edge joining them, as it will generate the cycle in tree structure. Let's understand all these steps with the help of an example. This is the graph structure for which we'll try to generate a minimum spanning tree using C programming language. As discussed earlier, primarily we'll create a sorted list of all edges in increasing order of their edge weights. The list will contain the source node, destination node, and corresponding edge weight for that particular edge. Along with that, we are going to maintain disjoint sets to carry out union operation. Those disjoint sets are parent and rank, and they will include rank value and parent value for every node in our graph. Initially, all the nodes are in their own different sets. Hence, we'll set their parent values to -1. Also, the ranks for these nodes will be initialized to 0 at the beginning because we haven't included them in our minimum spanning tree. Having said that, let's include the nodes of our graph in our MST. In upcoming slides, we'll traverse through our list of edges to include them in our minimum spanning tree. Now, the first edge that we are going to check is edge DC, which have minimum edge cost, that is 1. In order to insert this edge in our MST, we'll need to find the absolute parent of node D and C as well. So let's check out the parent set to determine the absolute parent value of node D and C. The parent value of node D is -1 and parent value of node C is also -1. Both of them are having same ranks, which means either we can make node D point to C or node C point to D. Here, I'll assume that node D points to node C. So, if node D is pointing to node C, then the parent of node D will become node C. And as C becomes the parent of node D, the rank of node C will change. Remember, whenever two disjoint tree structures are joined together, then the rank of one being pointed to will increase by 1. Hence, the rank of node C will become 1 now. Once the disjoint sets are updated, the union operation will generate the link between node D and C. Now, we'll process the second edge in our list, that is edge CB having weight 2. Primarily, we'll check the parent values of both these nodes. Node B and node C have parent values -1 and -1, which indicates that these nodes are absolute parent of their own sets. Since they have different absolute parents, we can join both of them. However, the rank of node C is higher than node B, thus the connection should point from node B to node C. As node B is pointing towards node C, thus node C will become the parent of node B as well. Hence, we'll update the corresponding absolute parent values for them. Next up is edge BA with the weight value 2. Now the parent value for node A is -1 and the parent value for node B is C. So both of them have distinct parent value, which implies that we can establish a connection between them. For that purpose, we'll have to update the rank field. And as the parent of node B is node C, the rank of C will definitely increase by 1. Once the fields are updated, the edge will get included in our MST. On that note, we have generated our minimum spanning tree, but you must be thinking about how our algorithm will discard the other edges. So to understand that, we'll traverse further in our list of edges. The next edge is edge AC, and the parent of node A is node C itself. Hence, we'll discard this node as well. Now the final edge in our list is edge AD, and again, both these nodes have the same parent node. Thus, we'll discard this node as well. Now, you must be thinking about how we can limit iteration of the whole list if we formulate MST using the few topmost edges only. Well, the answer to that is pretty straightforward. we can avoid the complete traversal of the list by using looping condition from e is equal to 0 to e is equal to mod of v minus 1. When we use this condition, the looping will stop when v minus ages get included in our MST. Now the next up is the time complexity analysis of Kruskal's algorithm. The time complexity of Kruskal's algorithm will be big O of E log E plus E log V. The E log E for sorting all ages and E log V for finding the age from maintained 3 sets. The average time complexity graph for this implementation will be something like this. It will be of parabolic nature. I hope that you all have understood the strategy for implementing Kruskal's algorithm. So, without wasting any time further, let's visit the code editor to develop a program in C programming language for Kruskal's algorithm.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by SimpliLearn. Click on the link in the description to know more.
Now, to begin with coding implementation, the first thing that we'll do is we'll create a storing system to represent a weighted age. For that purpose, we'll use structure in the C programming language. So let's get started with that. Struct age, and inside this structure, we'll create int source, destination, and weight. Now, what we'll do is we'll utilize this structure to store the ages of the graph. Moving ahead, we'll also initialize the structure for storing the complete graph. So let's create one more structure and we'll name the structure as graph. And inside this graph structure, we'll create node. We'll also create variable e to represent number of edges in our graph. We'll also call the reference of structure edge to this graph. By doing this, we'll be able to include all the edges into our graph structure as well. So let's create that reference struct edge star edge. Now we have successfully created the structure for graph. Now moving forward, what we'll do is we'll assign dynamic memory to the reference of graph structure. For that, what we'll do is we'll write code struct graph star generate graph, and inside this function we'll pass int node and the number of edges, that is e variable. Now we'll write body for this function, and inside body, first thing what we'll do is we'll create the space, that is dynamic memory space for this graph structure. Equal to struct graph star malloc size of struct graph. Next, graph dot node will be equal to node and graph dot number of edges will be equal to E itself. Next, what we'll do is we'll allocate a memory to each edge. Okay, I added underscore here. For that, what we'll do is we'll use struct edge star malloc size of struct age, and finally we'll return the graph. Now we have successfully allocated memory space to our graph and individual edges as well. So moving forward, what we'll do is we'll initialize one more structure to store the parent array and rank array. Basically, these are the disjoint sets whose usage will allow us to generate a spanning tree using union find algorithm. So let's get started with that. We'll create another structure and we'll name this structure as tree underscore maintenance underscore set, and inside this structure we'll create parent array and rank array. Now we have created the tree maintenance set structure, so let's generate an union find algorithm for maintaining MST structure. In order to do that, let's create a function named find disjoint set first. So this find disjoint set function will be of int data type find underscore disjoint set, and inside this we'll pass struct tree underscore maintenance underscore set, and its object subsets and a variable int I. Inside this function, we'll use if case to find root and make it as a parent of argument I. Also, if it is -1, then we'll need to update it. For that, we'll keep recurring through this if block by calling the function find disjoint set inside if block. So let's do that. If subsets I dot parent is not equal to I, then what we'll do is we'll get inside this if block and we'll execute subsets I dot parent is equal to find underscore disjoint set, and we'll again pass same argument subsets comma subsets I dot parent. and finally we'll get out of this if block and will return subsets I dot parent. Now we'll create a function for union operation. Let's name this function as void union underscore disjoint set, and inside this we'll pass struct tree underscore maintenance underscore set and its object subsets, and we'll pass argument x and argument y. Now inside this function we'll create two variables named xroot and yroot, and the xroot variable will store the return data from find disjoint set when the x has been passed to the function, and similarly the yroot will store the return value for find disjoint set given y as an argument. So let's write command for that. Int xroot will be equal to find disjoint set and objects will be subsets comma x. Similarly int yroot will be equal to find disjoint set and object subsets and variable y. Now, in order to build connection between these nodes, as discussed previously, the node with lowest rank value should always be pointing to the node with highest rank value and vice versa. So we'll have to use this if block in order to put this condition in the connection building block of our program. So we'll write condition for that here now. If subsets xroot dot rank is less than subsets yroot dot rank, then what we'll do is we'll set subsets xroot dot parent to yroot. That means okay. So what we are doing here is we are checking the rank value of xroot. If the rank value of xroot is smaller than yroot, then what we'll do is we'll simply set the yroot as parent of xroot. I hope you guys are clear with this. Now moving forward, we'll write else if part of this condition, else if subset xroot dot rank, sorry, I'll have to add s here, and if subsets xroot dot rank is greater than subsets yroot dot rank, then what we'll do is we will set subsets yroot dot parent is equal to xroot. Otherwise, if both above mentioned condition fail, then what we'll do is we'll add one more condition. We'll set subset yroot dot parent to xroot, and then we set subset xroot dot rank to incrementation. There is one mistake over here. Subsets. Okay. So now we have implemented the union find algorithm for this Kruskal's implementation. Next, we'll create a function to sort the list of edges in our graph according to increasing order of their edge weights. So let's create new function for that. We'll name this function as int my comparator, and inside it we'll pass const void star a and const void star b, and we'll create function body. But before we get started with coding implementation of this myComparator function, I want to talk about arguments of this function. So basically, a and b are constant quantifiers. The significance of this quantifier is to tell the user that you cannot modify this pointer and the location it is pointing to throughout the program. So let's get started with the coding part of this myComparator function. What we'll do is we'll create struct age star a1 is equal to struct age star a semicolon, and similarly struct age star b1 will be equal to struct age star b. Next, we'll return the output a1 dot weight is greater than b1 dot weight. So basically what this statement will do is, if the weight value of a1 is greater than b1, then it will return a1 as output, and if the weight value of b1 is greater than a1, then it will return b1. I hope you guys are clear with this myComparator function. So moving forward, we'll finally create a CrystalMST function. The return type of this function will be void, and we'll name this as CrystalMST, and inside it we'll pass argument struct graph star graph, and we'll create function body. Now the first thing that we'll do here is we'll assess the value of number of nodes in a graph, and after that we'll generate a new reference of structure age for storing our MST. So the first thing, we'll get the node to graph dot node and struct age result node. Along with it, we'll also initialize variable e and variable I equal to 0. So int e is equal to 0 and int I is equal to 0. We'll need to break the indentation here and here as well, and semicolon. So basically these variables will store index values for result and index variable for the sorted list simultaneously. Now moving forward, we'll sort all the edges of a graph. If we are not allowed to change the given graph, then we can create a copy of the given graph. The function named qsort allows us to do that. So let's create that qsort function here. Qsort graph edge, comma, graph e, comma, size of graph. H 0. So this qsort is nothing but C standard library function that implements a polymorphic sorting algorithm for arrays of arbitrary objects according to a user provided comparison function. And that comparison function is nothing but this myComparison function. And I guess you guys must be clear with this qsort term. So let's add comma here, and we'll give call to a myComparator function. Now moving forward, we'll break the indentation and we'll call the object of tree maintenance set underscore maintenance set star subsets equal to struct tree underscore maintenance underscore set star malloc node star size of struct tree underscore maintenance underscore set and we'll add semicolon here. So next we'll create subsets equal to number of nodes, and after that we'll make sure that all the elements have the rank value equal to 0, and to do that we'll initialize new for loop. So let's create for loop here. We'll begin it from v is equal to 0 to v is less than node and we'll set this v to incrementation. After that we'll make body for this for loop, and inside it we'll set subsets v dot parent is equal to v and subsets v dot rank is equal to 0. Now moving further, we'll traverse through all the edges in the graph, but we want to limit our traversal to the number of vertices minus 1, and to achieve that we'll create while loop here. While e is less than node, capital node, then node minus 1 and I it's smaller than graph e then create struct age next underscore age equal to graph dot age I plus plus, and here we'll create x and y nodes. So let's do that. Int x will be equal to find underscore disjoint set, and we'll pass subsets comma next age dot source, and for y we'll pass find underscore disjoint sets subsets comma next underscore edge dot destination. Now if including the edge between x and y does not create the cycle in our graph, only then we can include that edge in our MST. For that, what we can do is we'll set if x is not equal to y, Then we'll set result e plus plus equal to next underscore edge, and we'll find union disjoint set for subset, and we'll pass x and y as well. With this, we have successfully created our Kruskal-Semestick function. Now what we'll do is, we'll also print the structure of our minimum spanning tree. For that, we'll need to create pattern using printf function. So let's do that. The first statement that will print on screen is edges created in MST are as below, and we'll add \n so that our output gets to the next line. We'll add semicolon, and to that we'll add int minimum cost variable, and we'll initialize it to 0. So okay, so what we'll do is, we'll create for loop here, and we'll initialize it with iterator element beginning from 0 till I less than equal to e, and we'll iterate this I element. And what we'll do is, we'll create pattern for printing the edges. The pattern will go like modulus d dash dash modulus d equal to modulus d slash n, and the parameters that will get printed will be result I dot source comma result I dot destination, and result I dot weight. Okay, so we haven't added comma here. Now this error will get resolved. Now after this, what we'll do is, we'll increment this minimum cost variable by adding the values of edges to it. So we'll take this minimum cost variable, and we'll add result I dot weight to it. Now we'll get outside this for loop, and we'll printf one more statement. The cost for creating MST is modulus d, and will print minimum cost. Okay, we have now successfully implemented Driscoll's algorithm function, and we have created code for printing it on console as well. So now moving forward, we'll work on our driver method, and for that let's get into its function body. Here first we'll define the number of nodes that we are going to use for our graph. Those number of nodes are 4. The graph structure that we are going to pass to this Driscoll's algorithm program is the same that we have discussed implementation strategy for. It had 4 edges and it also had 6 edges as well. So we'll add 6 edges here. Now what we'll do is we'll set struct graph star graph equal to generate graph, and we'll pass node comma e, and we'll add semicolon. Now next we'll create graph structure by implementing the edges. So the for first edge we'll call graph dot edge 0 dot source will be equal to 0. That means the first edge will begin from 0 and it will end at destination node, and that will be 1. And the weight for this edge will be equal to 2. Now we'll copy this pattern and we'll paste it below. Okay, and now the edge will be 1, and for this edge 1 the source will be 0 and destination will be 2 and the weight value will be 4. Now let's copy this again, we'll paste it and we'll set edge number to 2. We'll change source and destination. Now source will remain same and destination will be changed. We'll make it 3 and the weight value will also remain the same. That means edge between 0 to 2 and edge between 0 to 3 have same edge weight. Now for next, Control V, we'll remove this indentation and now we'll change the node number, edge number. Here the source will be 1 and destination will be
3 and the age weight value will be 3. After this, we'll add new age. The age number will be 4 now. The source will be 2 and destination will be 3 and age weight will be 1 and the last age will be age 5 and the source will be 1 here and destination will be 2. The age weight will be 2. Now after this, what we'll do is we'll give call to our critical MST function in order to generate minimum spanning tree, and we'll pass this graph structure to it and we'll add return 0 statement. With this, we have successfully completed our programming implementation for Kruskal's algorithm. So let's run it and check if our code is working fine or not. Okay, so we are getting 3 problems here. The first one is expected token. Oh, so int node will be equal to graph.node, and this node should also be capital here. Okay, so what next error is there? Yeah, so now our code is bug free. Oh, but some exception is happening here. We'll jump this exception. We'll try to jump it. Okay, but we are not having any errors into our system, so I think that's the compatibility issue with our VS Code. So let's copy this code and paste it into the virtual coding environment, and we'll check it if this code is working fine or not. So we'll copy the code and we'll go back to the Google Chrome. We'll go to the online compiler tool, and here we'll paste our code and we'll run it. Okay, so here we are getting our output. So there will be only 3 edges that will get formed in our minimum spanning tree, and the cost for all those edges will be 5. I hope this coding implementation is clear to all of you out there. If you're concerned about this code, then don't be, as we can send it over to you if you drop your email IDs in the comment section below. So drop your email IDs in the comment section below in order to receive this code.
Backtracking is an algorithmic method of alternately solving a problem. To explain the issues, it employs a recursive approach. Backtracking is required to find every possible combination to solve an optimization problem. Backtracking is used in solving various problems like n-queens, knight's tour, the rat in the maze problems, and so on. Now, to get better understanding of backtracking, let's have a brief look at n-queens problem. Let's say we have 4 by 4 matrix. We have to place 4 queens in that. Every row and column has exactly 1 queen and none of them falls under the same diagonal. We will start with the leftmost column. Then we will check our base condition that if we have placed all the queens or not. Now we will try every row in this column. If we found a location where the queen can be safely placed, then we will mark it as a part of an answer. And then we will recursively check if placing queen here will lead us to the solution or not. If yes, then we will return true. Otherwise, if false, then we will backtrack and try other rows and repeat these steps. If all rows have been tried and nothing worked, then we will return false to trigger backtracking. Now let's implement this n-queens problem in the code editor. We will define a vector. Inside a vector, it will be an int vector result. Now we will write a utility function to check if the queen can be placed on board. So it will be a boolean function. Bool is safe. As argument we will place a vector inside a vector. Int board, comma, int row, comma, int column. We'll define int I, comma j, int n will be equals to board size. Now we will check if this row on the left side. So for loop I is equals to 0, I less than column, I plus plus. If board at row I then we will return now we will check upper diagonal on left side. So for I is equals to row, comma j is equals to column, j greater than equals to 0, and I greater than equals to 0, I minus minus, comma, j minus minus. If board I, comma j then return now we will check lower diagonal on left side. So for I equals to row, comma j is equals to column, I less than n, and j greater than equals to 0, I plus plus, comma, j minus minus. Now if board at I and j will return else we will return Basically, what we have done in this function is we have checked that row and the right diagonal and the left diagonal so that no queen can overlap. Now, next, we will write a recursive utility function to solve n queens problem. So, bool solve nq. Its argument will be vector inside a vector int ampersand board comma int column. Now we will first check our base case if all queens are placed. So int n is equals to board size if column is equals to n. Then we will define a vector int b. So for int I is equals to 0, I less than n, and I plus plus. Another nested for loop int j is equals to 0, j less than n, j plus plus. If board at I and j is equals to 1, then v dot push back j plus 1. Now we will print result dot pushback and we will return true. Now we will consider this column and try placing this queen in all rows one by one. So boolean res is equals to false. Now for loop and I is equals to 0, I less than n, I plus plus. Now we will check if queens can be placed on board I and column call. So if is safe board I call, if it's safe then we will place this queen at that position. So board I call is equals to 1. Now we will make result true if any placement is possible. So res is equals to solve enqueue at board comma call plus 1 or res. Now if placing queen in board I call doesn't lead to a solution, then we will remove the queen from the board I column and backtrack. So board Now if queen cannot be placed in any row in this column, then we will return false. So return plus. Now this function solves the n-queen problem using backtracking. It is basically using solve enqueue to solve the problem. It returns false if queen cannot be placed, otherwise returns true and print placement of queens in the form of ones. Now, there may be possibility that there are more than one solution. Then this function will print one of the feasible solution. Vector, write a vector and queen int n result dot clear. Now we will call vector inside a vector
board, n, comma, vector, int, bracket n comma 0. Now if solve nq at board comma 0 is false, then we will return empty set. Otherwise, we will sort result dot begin comma result dot end. And we will return result. Now we will write the main block. So int n is equals to 4. So for vector, inside vector, int v will be equals to n queens at n. So we will write for loop auto ar v we will call cout then for loop auto itr ar cout itr and cout. And then we will return 0. Now let's run this code. As you can see, we are getting 2 answers. Now this n queen can be solved with both of these answers. Now let's get back to our slides. At last, let's sum up what we have learned in this session. First up, backtracking is simple to implement and has fewer lines of code. Most backtracking codes are composed of few lines of recursion function code. Next, since we use recursion, the function information is stored on the stack, which has high space complexity. Next, when the branching factor is significant, it is very time consuming in many cases. Finally,
Many problems such as knight steward and queens, rat in the maze, subset sum problem, and so on can be solved using backtracking.
Choose from over 300 in-demand skills and get access to 1,000 plus hours of video content for free. Visit SkillUp by SimpliLearn. Click on the link in the description to know more.
We will have a look at an application of the spanning tree to understand it better. Meet Patrick. Patrick works as a head of the network administration department in an IT solution company named as Gray Solutions. Being the head of network administration department, Patrick is responsible for managing his team to keep the organization's computer network up to date and operate it as intended. Network administration department coordinates and connects multiple systems in the company to a single network using multiple routers. This network is called as local area network or LAN, which is created for the sole use of an IT company. But in the last few days, something went wrong in the network management system which came to Patrick's notice. He observed that the network loop is formed in a routing system. A network loop occurs when multiple routes carry information from the same source to various computing devices. And due to this formation of a network loop, the network connectivity started slowing down initially. After a few hours, the network connectivity completely went down and all the operations of the company stopped abruptly. Now Patrick and his team needed to do something in order to resolve this problem permanently. So Patrick started brainstorming to find out an optimal solution to fix this problem. One of Patrick's teammates was good at data structures and he came forward with an idea to implement a spanning tree data structure for managing the routing connections. He suggested replacing the old naive routing strategy with a minimal spanning tree routing. After listening to this idea, the whole network administration team started working on implementing a spanning tree. While doing that, they treated the network connection as a graph. The routers and end devices like computers, fax machines were treated as the nodes of the graph, where the connecting wires carrying network signals were treated as the edges of a graph. But before understanding how Patrick's team was able to solve this problem using a minimum spanning tree, let's first understand the basics of this data structure. This will allow us to get a clear insight into how spanning tree solves network routing problems. So let's start with graph and its different types. Basically, a graph is a structure made of nodes and edges connecting them. And there are three types of these graphs based on the types of edges. The first is the undirected graph, the second is the directed graph, and the last is the connected graph. Let's understand these types completely in the upcoming slides. The first type of graph that we are going to discuss is the undirected graph. It is termed as a graph in which all the edges does not point to any specific direction. In simpler words, all the edges of this graph will be bidirectional. As you can see in this particular graph, you can move from any node to any other node and retrieve back as well. Next up is the directed graph. It is a graph in which the edges point to a specific direction. By this, I mean in this type of graph, you can only move towards a single direction. For example, you can traverse this given graph starting from A, then B, then C, then D, and finally E. But here, you cannot traverse back from E to A as this graph is unidirectional. The last type of graph, depending on its edge, is a connected graph. It is defined as a graph with a path from any vertex to any other vertex in the graph. In this particular type of graph, you can reach any vertex from any other vertex in a graph. For example, you can go to node B or D from node A and arrive back at A from either vertex B or D. Now moving ahead, we will understand what a spanning tree is and how we can create it. Mathematically, the spanning tree for any graph G having vertices V and edges E can be represented using superscript notation G' having vertices V' and edges E'. Suppose we intend to create a spanning tree for graph G, then our spanning tree G' must follow few constraints. The first constraint suggests that the number of vertices for created spanning tree must be equal to the number of vertices of a given graph G. Further, the edges of G' should also be similar to the number of vertices in graph G minus 1. To understand this mathematical formulation clearly, let's have a look at an example. Now, for this given graph G, we have to formulate all possible spanning trees. Remember, a single connected graph can have multiple spanning trees until we fulfill the constraints mentioned earlier. So for this particular graph G, we have 5 vertices and 5 edges. Additionally, each edge has been assigned with some cost or weight. Let's say this weight represents the distance between the connected two nodes. To create the spanning tree G', we need to ensure that G' contains 5 vertices and 5 minus 1, that is 4 edges. Hence, for this graph, we can create a spanning tree like this. You can observe that we have eliminated one node in the spanning tree to remove the loop or cycle in a graph. For this spanning tree 1, we have a cost or value equal to 10. And this cost is nothing but the summation of all edge weights. Now that we have created the first spanning tree for our graph G, I would like to ask all of you to give this a try. For that, I am going to provide you with a short moment to generate all possible spanning trees for the structure that we are discussing right now. You can also pause this video if you need more time in order to do that. So now let's have a look at all possible spanning trees at a glance. We have seen that the value for the first spanning tree was 10. And for this new spanning tree 2, it is 13. In this spanning tree, the edge between vertices B and C is removed. The next spanning tree looks something like this with cost 14. Further, we have spanning tree number 4 with a value 12. And finally, we have the last possible spanning tree 5 with a value 11. Out of all these spanning trees, the value or cost for spanning tree number 1 is the least, which is 10. Thus, this spanning tree will be called as minimum spanning tree. I hope you're clear with the creation of spanning trees. But how can we judge the number of all the possible spanning trees? Well, for that you need to check the structure of your graph. If the graph you have been given with is cyclic, then the number of possible spanning trees will be equal to the number of vertices. The cyclic graph is a graph in which you will have the same number of vertices and edges with a cyclic structure. If the given graph is a complete graph, then the number of possible spanning trees will be equal to v raised to v minus 2. Where v is the number of vertices in a given graph. You can say that the given graph is a complete graph if each pair of vertices is connected by the unique edge. For this particular graph, the number of possible spanning trees will be equal to the number of vertices, that is 4 to the power of 4 minus 2, which is further equivalent to the square of 4. Hence, the number of possible spanning trees for this structure will be 16. Moving forward, let's understand some important properties of spanning tree. We have already gone through some crucial properties while creating spanning trees in the previous section. So primarily, we will list all of them here. The first property of a spanning tree conveys that a connected graph can have more than one spanning tree. The next property states that the number of vertices in spanning trees must be equal to the number of vertices in the given graph, whereas the number of edges is equivalent to the mod of v minus 1. The third property of a spanning tree says that the spanning tree must not contain any cycle. If the structure that you have created as a spanning tree includes a loop or a cycle, then it's clear that you have made a mistake because no tree can contain a cycle. And finally, the fourth property is all about Cayley's formula. If the given graph is a complete graph, then you can calculate the number of possible spanning trees using the formula v raised to v minus 2. The next property of a spanning tree conveys that a spanning tree can never be disconnected. For example, if you create a spanning tree for this given graph which is accurate and you erase one edge, when you do that, the structure will no longer be a spanning tree. It can only be referred to as a disconnected graph. The next property states that if the graph contains more than one similar weight, there is a possibility of having more than one minimum spanning tree. For example, in this particular graph, there are more than one edge having the same weights. Thus, there will be two possible minimum spanning trees with the same cost, that is 7. This is all about the properties of spanning trees. Now that you understood what spanning tree is, you would have also understood how it proves is an effective solution, and that is exactly how Patrick from our story solved his network issue. In a few days, Patrick and his team changed the naive routing into the minimum spanning tree routing. Now, the routing paths are managed by a minimum spanning tree to maintain cost effectiveness and to avoid any looping activity. As we have already understood, MST removes all the loops from a given graph, and we also know that the whole network becomes the graph for which MST will maintain a minimal routing path. Hence, the network system will never experience a network loop again. Due to this amazing initiative, Patrick and his team were appreciated by the whole organization. This example clearly illustrates the importance of a spanning tree and why it is one of the most important algorithms in data structures. Now we will look into the different applications of spanning trees. The first application that we are going to talk about is telecommunication network building. If we want to build a telecommunication network for the whole city and we are putting different connection lines for each customer, then we will have to deal with a huge cost. This naive, ordinary approach is not the best solution to build a connection line. But no worries, this problem can be resolved using the minimum spanning tree data structure. In this case, each customer will be treated as a vertex, whereas the connection line will be treated as an edge. The minimum spanning tree will give us the possible output for generating the telecommunication network. No matter what type of algorithm you are building using machine learning techniques, somewhere down the line you will be using clustering techniques quite liberally. Clustering and data preparation go hand in hand, as many times you will be working at least initially with data sets that are largely unstructured and unclassified. Those data sets cannot be classified using single neuron or classification methods. So you use a clustering algorithm which utilizes a minimum spanning tree to create clusters or groups by mapping distances between data points. The next application of a minimum spanning tree is image segmentation. You must have observed that your face gets detected with a square shape while clicking images in selfie mode. This scenario is happening due to the image detection algorithm developed in the camera system. At the back end, the picture gets fragmented into tiles of similar pixels with the help of a minimum spanning tree. The last application of the spanning tree is its use in calculating the finance factors. A correlation matrix can be created by calculating a coefficient of correlation between any two stocks. This matrix can be represented topologically as a complex network, and a minimum spanning tree can be constructed to visualize the relationships.
So what exactly is breadth-first search algorithm? So breadth-first search algorithm visits every node efficiently and marks all the nodes which are adjacent to that particular node. The critical nodes in the graph are in a breadth-wise manner. Breadth-first search starts traversing from root node and then selects all the unvisited adjacent nodes of the selected node. Queue data structure is used to implement BFS algorithm. So here you can see a GIF which is explaining about BFS algorithm. So let us consider that we have selected the root node as 1. Then it will check for all possible adjacent nodes. So it will traverse to 2, then it will traverse to 3. After that it doesn't have any adjacent nodes. So the control moves to either one of the child nodes, that is 2 or 3. So let us consider that we go to 2. And from 2 it will check for all the adjacent nodes, that is 4 and 5. And there are no other adjacent nodes from 2. Then it will go to 4. It can also go to 5, but here let us consider that it goes to 4. So from 4 it does not have anything to traverse, so it gets back to 2. Then it goes to 5. And from 5 it checks for the traversal. There is only one possibility, that is 7, and no other explorations. Then it goes to 7, and there is no other possibility for 7 as well, so it comes back to 5, then to 2, then to 1, and then it enters the second child node, that is the 3. From the 3, it moves to another possibility, that is 6, and it checks for another possibility, but there is no possibility. So now the control moves from 3 to 6. From 6, it tries to visit the adjacent nodes. So 6 has only one adjacent node, that is 8, and no other adjacent nodes. And now from 6, it goes to 8. And from 8, it checks for any other adjacent nodes, but there is no other adjacent node, so it gets back to 6, then 3, then to 1 back. So this is how the control traverses when you are implementing breadth-first search algorithm. Now here, let us look into an example for breadth-first search algorithm. As discussed in the previous example, here the root node is selected first. Then it goes to B. Then it goes to C. and it checks for any other adjacent node, but there is no other adjacent node other than B and C. So the control moves to B, and from B, it starts traversing to all its adjacent nodes. First, it traverses to D, then to E, and it checks for any other possibility, but there is no other possibility. So the control goes back to B, then to A, and from A, it traverses to C. And from C, it checks for all the adjacent nodes, that is F and G. So it checks for other possibilities. Since there is no other possibility, it goes through F, and from F it checks for other possibilities, but there are no other possibilities from F. So the control gets back to C and then finally to G. And in G, it checks for any adjacent nodes. Since there is no adjacent node from G, it stops there, and we have the queue output here, that is A, B, C, D, E, F and G. So this is how the breadth first search algorithm works. Now to understand this in a practical way, let us try to execute a program in Dev C++. So now we are on Dev C++ and the program on my screen is an example for BFS algorithm. In this program, we have a queue first, as BFS is executed using queue data structure. And there are two variables, that is rear and front, and there is one array named as size, and the size is defined here as 50. Next, we created some functions. First, there is a queue function to create a queue. Then we have enqueue and dequeue to insert and delete the element from the queue. So this is the enqueue function and this is the dequeue function to insert and delete the elements from the queue. Then we have a function to display, and after that we have the empty function to check whether a queue is empty or not. So this particular code segment is to check whether the queue is empty or not, and this particular function is the print function, which is used to print the elements inside the queue. After that, we defined node and made a function as creating a node, and in node there is a one variable named as vertex and one pointer next to it. So this is the structure for creating the node, and followed by the node we have created another structure called graph, and inside graph we have the create graph function to create the graphs, and we have number of vertices, adjacent lists and visited. And next we have the add edge, where we will add edges in between the vertices. And finally we have the BFS algorithm. So here we will check if the queue is empty or not first, then we will call the dequeue function and we will execute the BFS algorithm. And now finally we have the main function, where we will add all the edges to the graph and call the BFS algorithm. Now let's try to run this program and see the output. So there you go. The program got successfully executed and the output is displayed on the screen. So queue contains the values, that is 0q, reset node is visited to 0, and then queue contains values 2 and 1, now the node is visited to 2, followed by that the queue has values 1 and 4 and node has visited 1, and then queue contains values 4 and 3 and node has visited the value or vertex 4, and finally queue contains value 3 and the queue is reset and the node is currently visited at node number 3. Now with that, let's move ahead into the next type of algorithm, that is the depth first search algorithm. So what is depth first search algorithm? So DFS algorithm is used for traversing trees using the depth-wise direction. The execution of this algorithm begins with the root node and explores each branch before backtracking. Next, DFS uses stack data structure to remember to get a subsequent vertex and start a search whenever a dead node appears or the dead end appears at any iteration. Now we used to have queues in BFS algorithm, but in DFS algorithm we will be using stacks. Now to understand the working of depth first search, let's go a bit more detail. So here we have a graph. So how depth first search algorithm works? Now here we can choose the root node first. So once the root node is chosen, it sees the possibilities of traversal. It starts from the left side tree first. It first visits B, and now it will not stop at B. In BFS, it used to stop at B and used to check all the possibilities. But here it is not like that. It will first visit B, then it will not stop at B. It directly sees the depth of the B, that is, it has another child node. So it will enter the left child node and checks D. And now here it will not stop at D. It will check for possibilities at D. So since there are no possibilities from the left or right side of D, it will get back to B. And now it will check for another possibility from B, that is right side. First it finishes the left subtree. On completion of left subtree, only then it will enter the right subtree. So here it checks for the possibility. It found E, and from E it will check for another depth search. So there is no depth search from E, and not on left and not on right, so it comes back to B. From B it visits the root node again. From here it checks for the right subtree now. Here we have C. So it will not stop at C, it will go to the next subtree, that is F. And now it will not stop at F, it will search for other opportunities. Now since there is no other opportunity or other vertex from F, it gets back to C. And after that, it checks for next right subtree, that is G. So from G, it looks for another opportunity or vertex. Since there is no other vertex, it gets back to C, then to A. So to keep the traversal in order, it uses stack data structure. Now for a better understanding, let us go through a practical demo on Dev C++. And now we are on Dev C++, and this particular code is an example for DFS algorithm. In this particular code, we have defined the structure, that is node, and inside the node structure we have this vertex and node reference, which points to the next node in the graph. Followed by that we have the graph structure, and inside graph structure we have the number of vertices and visited and reference to each node. Followed by that we have the depth first search algorithm, and this particular code segment is the logic for depth first search algorithm. Then we have the structure of node reference, and followed by that we have the structure of graph reference, that is the number of vertices visited and the adjacent vertex list, and then the reference if that particular node is visited or not. Now we are using dynamic memory allocation here, and followed by that we have add edge function where we will add edges between the vertices, and followed by that we have the print graph function. So here we will be printing the stack data structure which has the vertex after visiting all the vertices in the graph. And finally we have our main function where we will assign the edges to the graph. Then we will call the depth first search algorithm. Now let's try to execute this code and see the output. There you go. You can see that the code got successfully executed, and we have our list here. That is, we have visited the vertex 2, 3, 1 and 0. Now followed by this, let us look into the differences between breadth first search and depth first search algorithms. So some of the fundamental differences are: breadth first search finds the shortest path to the destination, whereas depth first search goes to the bottom of the subtree and then backtracks. The next difference is BFS algorithm uses a queue to keep track of the following locations to visit, whereas DFS algorithm uses stack. Now we have gone through that in the examples for both DFS and BFS. Followed by that, the next difference is the BFS uses FIFO, that is first in first out order of implementation, because we are using queue data structure here. Whereas DFS uses last in first out order of implementation, because we are using stack data structure. The next difference is BFS requires more memory as compared to DFS, and depth first search requires less memory compared to that of BFS. Followed by that, we have BFS algorithm which gives the shallowest path to the solution. Next, compared to BFS, DFS algorithm does not guarantee for shallowest path as the solution. The next difference is In BFS algorithm, if you do not find any goal, then you may need to expand to the other nodes before the solution is found. Whereas in DFS, if you do not find any goals, then the backtracking will start from the leaf node. Now we will discuss some of the major applications of BFS algorithms. So BFS algorithm can be easily used to create the shortest path and the minimum spanning tree to visit the graph vertices in the shortest time possibly with high accuracy. BFS algorithm is implemented to locate all the neighboring nodes in peer-to-peer network, and this will find the required data faster. Search engine or web crawlers can quickly build multiple levels of indexes by employing BFS algorithm and start implementing from the source, and then it visits all the links from the source. The BFS algorithm guides the broadcast packet to find and reach all the node it has for the address. Now we will look into the applications of DFS. The next application of DFS is, it is primarily used for scheduling jobs for the given dependencies among the group of jobs. In computer science, it is used for instruction scheduling, data serialization, and compilation task ordering. Next, the DFS algorithm can be easily adapted to search all solutions to a maze, including nodes in an existing path in the visited set.
The breadth-first search approach repeats the procedure for all the nodes until the desired node is found. The queue data structure is the data structure that is used for breadth-first search algorithm. For a better understanding, we look at an example of breadth-first search algorithm. The blue color indicates that the node has been already explored, while the pink color indicates that the node has not been explored yet or visited yet. Next, we'll have our output. We will use a queue data structure to keep track of all the nodes visited and all the nodes that are unvisited. So, to begin, let's look at the algorithm. As a result, we'll have node A, which is added to the output and marked as visited. We must verify all the unvisited adjacent nodes of A, that is node B and node C, and add B and C nodes to the output and enqueue to the queue according to the breadth-first search algorithm. Then, we'll look at any node between B and C. We'll start with node B. Node D is unvisited, adjacent to node B, so we'll add node D to the output and queue. And since node B is now being visited, we'll dequeue it. When it goes to node D, the next unvisited node is node E. Add node E to the output and enqueue to the dequeue. Once node D has completed its traversal, dequeue from the queue. Now, in the case of node E, the adjacent node is node C, which is already visited. Thus, we will dequeue node C from the queue. Now that the pointer is pointing to node C and node F is the next unvisited node after the node C, we will set node F to output and queue. Here, the pointer leads to node F, which has no unvisited adjacent nodes. So, we will dequeue F from the queue and queue is empty. So we'll come to the halt here. Here's what we got, that is A, B, C, D, E and F. After understanding all the theoretical aspects of BFS algorithm, let's look at the code of BFS algorithm in C programming language. Now we are on the practical mode. On my screen you can see an example for BFS algorithm. We have declared a two-dimensional array with maximum row and column size of 10 and two arrays. The first one is a square of a maximum size of 10 and the second one, which is a visited, that stores the maximum size of 10 as well. Some variables n, I, j, and finally we declared front, which is initialized with 0, and rear variables, which is initialized with -1. We perform a loop from index 1 to the size of an array visited in this function, with the condition that if two-dimensional array of column 1 and visited array of index is not 1, we initialize variable I to the front of the queue. Then 1 is set as the front of the queue index of the visited array, and we use the breadth-first search function with the vertex as the front of the queue until front is less than or equal to rear. Then we enter the main function, where we define the variable x that stores the graph's vertex, and then we use the printf function to enter the number of vertex that will be stored in variable n. Then we perform a loop from index 1 to queue size and visited array, in which we initialize 0 to the queue and index 1 to the visited array. Then, after that, we'll enter the graph value in the form of matrix of two-dimensional array by performing a loop with two variables, I for the graph row and j for the graph column. Then we print the source node, which is saved in the variable x. Then we print the source node, which is saved in the variable x, and we call the breadth first search function or method, which takes a vertex x as parameter, and we print which nodes are reachable by looping from index 1 to the size of the visited array. If index 1 of the array is visited, otherwise breadth first search is not possible. So this was the explanation of the program. Now let's try to execute and see the output. There you go. The program got successfully compiled and now it's asking for the input. Now it is asking for the number of vertices. Let's enter the number of vertices as 3. Now it is asking for us to enter the input in the form of matrix. So the first row will be 1, 2 and 3. So these are the first rows. The next rows will be 2, 3 and 4. So the last row elements are 3, 4 and 5. So we have successfully given all the 3 rows of elements. Now let us select the source node. So the source node would be 2. Now all the nodes that are reachable from the source node 2 are 1, 2 and 3. So there you go. That's how you implement the breadth first search algorithm. So what is a depth first search? So basically, a depth first search is an algorithm for traversing or searching the tree or graph data structures. The algorithm starts at the root node, selecting some arbitrary node as the root node in case of graph, and explores as far as possible along each branch before backtracking. So DFS starts with the initial node of the graph, then goes deeper until it finds the goal nodes or the leaf nodes or the nodes that have no children. That is the end part. Here you can see 4 and 7 are the leaf nodes. So the depth first search algorithm runs till the end of all the nodes. That is 8, 10. All these are the leaf nodes or the last goal nodes. In DFS, the backtracking starts once all the nodes are explored. And the DFS algorithm uses stack data structure for its traversal. Now that was a brief introduction to the DFS algorithm. Now for a better understanding, let's go through a practical example. So here we have a graph data structure with elements A, B, C, D, E, and F. So we will be running the DFS algorithm and we will be traversing through all the nodes of this particular graph. And the traversal will be recorded using a stack data structure. And we have 2 different colors which will be used to indicate the element's color. So the black color is for the nodes which are not visited yet, and the blue color will indicate the nodes which are being traversed already. Now this is the stack data structure that we will be using for the traversal, and we have another part which declares or which gives out the output of the traversal of the nodes of this particular graph. Now we will begin with the first one, that is A. Now followed by that we will move ahead to B. Then after B we will go through D. Then after D we have E. Next we have C, and last we have F. So that's how we traverse through the graph using the DFS algorithm. Now for a little more understanding, let's go through a practical example where we will be executing a program for implementing the DFS algorithm. So this particular program on my screen is an example for DFS algorithm. So here we have the structure node. So followed by that we have also the methods which will create the edge and which will also print the graph elements. And finally, we have the main class. Now, don't worry about the code. This particular code segment or the complete code document will be added in the description box below, and you can have access to it and try to run it on your local system and have a better learning experience. Now, without further ado, let's try to run this program and get the output and see how the DFS algorithm gets implemented and traverses through the graph. There you go. The program got successfully executed and we had the graph elements, that is 0, 1 and 2 and 3. So it has visited all the elements, that is 2, 3, 1 and 0 according to the stack data structure, and we have found the output over here.
In this session, we will discuss shell sort. Shell sort is a sorting algorithm that is based on insertion sort algorithm, and it is very efficient. When the smaller value is on the far right and must be shifted to the far left, then this method avoids significant shifts as in insertion sort. Now let's discuss the algorithm of shell sort. Let's say we have an array. We will initialize a variable h. This h will represent intervals. Then we will divide this array into h intervals. It will create some subarrays. Then we will apply insertion sort on these subarrays. After that, we will reduce the interval h by 1. Then we will repeat this process recursively until h counts down to 1. We have now introduced shell sort and its algorithm. Now let's try to implement this algorithm in the code editor. First, we will start with a function to sort an array using shell sort. So int shell sort, we will write argument as int arr bracket comma int n. We will start with a big interval, then we will reduce this interval by 1. So for loop int interval equals to n by 2 interval greater than 0 and interval divide equals to 2. Now we will do a gapped insertion sort for this interval. So for int I is equals to interval I is less than n, I plus equals to 1, int temp is equals to arr bracket I. Now we will shift earlier gap sorted element up until the correct location for arr I is found. So int a. So for j is equals to I and j greater than equals to interval and arr bracket j minus interval greater than temp and j minus equals to interval. Now arr at j is equals to arr j minus interval. Now we will put this temp in its correct location. So arr bracket j is equals to temp. Now I will return 0. Now let's write a function to print this array. So void print array int arr comma int n. So for loop int j is equals to 0, j less than n j plus plus cout arr bracket j Now we will write the function for the main block. So int arr is equals to 12, 34, 56, 85, 2, 9, 11, 5. Now let's find the size for this array. So int n is equals to size of array divided by size of first element of this array. Now cout array before sort of print array arr n shall sort arr n. Now cout arrays after sorting. We will again print array arr n. Now let's try and execute this. As you can see, we have successfully sorted this array.
Here, we will look into the real-life example of greedy algorithm in order to understand it better. This is Alex. He's quite wealthy and intelligent as he works for one of the most reputed IT firms. And this is Alex's best friend Rachel. Rachel is in dire need of $85 right now. However, she needs money in such a quantity that the number of coins is kept to a minimum. So Rachel shared this issue with Alex and asked him for help. Now Alex is thinking about Rachel's issue, which he can easily fix because he has a limitless supply of $50, $20, $10, and $5 coins stashed in various bags. Although this being said, Alex needed to think about the constraint Rachel told him about. He needed to give her money such that the number of coins utilized must be minimal. To do so, Alex began making a list of the various coin combinations in which he could present money to Rachel. However, after a while he became confused due to the vast number of conceivable combinations. So he decided to use his programming ability to solve real-life problems. Alex developed a program that will provide him with the optimal number of coins that he can present to Rachel. This generated program was iterating through the different possibilities to choose the best solution. At each iteration, the program added the coin of the largest value that was not taking Alex past the amount to be paid, which is $85 in this case. For $85, the largest denomination ID can start giving is $50. Now, ID is still short of $35 to reach the amount so that the next largest coin program can take in as $20. But since the program still requires $15 to meet the threshold, the next highest denomination it can accept is $10, followed by $5. The best part about this program was that it allowed Alex to present $85 in just 4 coins, which is fairly incredible. The vital thing to note here is that after each loop, the program makes a greedy choice, providing the coin with the highest potential value. What I mean here by greedy is that locally optimal choice is picked at every step to reach the global optimum solution. Now moving ahead, we will formulate the idea of greedy algorithms. Basically, a greedy algorithm is based on a problem-solving method that involves making locally optimal decisions at each stage in the hopes of achieving a global optimum. That means at each stage we choose a locally optimal value in the hopes of arriving at the optimum possible end result. Furthermore, this algorithm is an optimization technique that can find either minimum optimum result or maximum optimum result. The best part about this algorithm is that it is simple to understand and implement as well. Additionally, the runtime complexity for this algorithm is pretty reasonable. However, the fundamental disadvantage of this strategy is that we only receive the globally optimum value in a small percentage of cases. Having said that, you must be thinking about when to implement this algorithm for solving particular problems, as it does not always produce globally optimum results. Well, let me tell you guys that we have 2 conditions to judge our problem for implementing greedy algorithms. The first condition is the greedy choice property. This notion states that making locally optimal judgments can lead to the global optimum solution for a given problem. The second condition is about optimal substructure. The problem has an optimal substructure only if an optimal solution to the entire problem comprises the optimal solutions to the subproblems. In simpler words, that means the problem can be split down into multiple subproblems, and the solutions to these subproblems can collectively lead to a solution for the entire problem. If both the above-mentioned properties are satisfied by the problem, then we can create a greedy solution for that particular problem. Moving forward, we will look into the steps for constructing a greedy solution. Finding the substructure or subproblem that can lead us to the final answer is the first step in building a greedy algorithm. Because in this algorithm, we are just trying to operate with local optima to reach the global optimum solution. The second step is about determining the type of solution the given problem can result into. That can be either the largest sum or minimum path. The final step for creating the greedy solution is about creating an iterative process for traversing through local stages and making decisions to reach a globally optimum solution. Now, you might be confused about how we can do that. Well, let's go through an example to understand the approach to implement a greedy solution. The example that we are going to deal with is called the traveling salesman problem, in which a salesman is supposed to reach the destination from a given current location. The representation of cities and paths connecting them is done using graph structure, where each node is considered as a city and edges connecting them as paths, having edge weight as the distance between the 2 cities. Now, in this case, we are supposed to find the minimum path between 2 cities. So to do that, we will begin from the current arbitrary position. From this node called as starting location, there are 3 possible paths, but the path towards city B has less distance. Hence, we will traverse this edge primarily as it is an optimal local route. We have reached city B now, and from this node we have 2 possible paths, out of which one path directly leads us towards the destination city having distance 20, but the other path leading towards the city F has edge weight value or distance value as 2. Hence, according to the local optimal decision, we will choose the edge connecting cities B and F for traversal. We have reached the city F now. From this node or city, there is only one path leading us to our destination. Hence, we will traverse it. Now we have reached the destination city. The path highlighted in the green shade is the global optimum for this TSP problem. You can verify that by calculating the edge weights for all other possible paths. Since this solution allows us to reach the global optimum by making optimal decisions at the local stage, this strategy to solve the problem will be considered a greedy approach. Now moving ahead, we will look into the demerits of using greedy algorithm. We have learned that the greedy algorithm makes decisions based on local optimum instead of analyzing the broader picture of the whole data. Hence, there is a possibility that the greedy solution might not be the best optimal solution for some problems. For example, consider this traveling salesman problem. In this problem, the highlighted part is a created solution to reach the destination city from the current location using a greedy algorithm. But if you observe this graph, the selected solution is not the global optimal solution for this problem. In contrast, it is the worst generated solution to reach the destination. That is why the greedy algorithm is considered to be prone to correctness issues. Even if the algorithm is correct, proving why it is correct is difficult. Thus, it is deemed to be trickier to solve specific issues. Now, we will discuss about applications of greedy algorithms to understand their importance. The first application of a greedy algorithm is its use for constructing minimum spanning trees. The coding approaches that we use to generate MSTs is based on the greedy algorithm. Both Prim's algorithm and Kruskal's algorithm are known as greedy algorithms as they make decisions based on locally optimal decisions. The next application of the greedy algorithm is its use to implement Huffman encoding and decoding algorithms. The Huffman coding technique is a lossless data compression method. The concept is to give variable length codes to input characters, the lengths of which are determined by the frequency of the related characters. The smallest code is assigned to the most frequently occurring character, whereas the largest code is assigned to the least frequently occurring character. This process is carried out by making local optimum decisions. Hence, it is also considered to be a greedy algorithm. The final application of the greedy algorithm is its use for developing solutions to well-known coding problems. Those problems are the activity selection problem, job selection problem, and fractional knapsack problem. All these problems generate solutions by making decisions at each local stage. So the solutions for these problems can be developed quite easily using the greedy approach.
The Prim's algorithm is used to find minimum spanning tree for a given graph. But what exactly is a minimum spanning tree or MST? Well, a minimum spanning tree is a subset of graph G having the same number of vertices as of graph G and edges equivalent to a number of vertices minus 1. Along with these properties, it also has a minimum cost for summation of all edge weights included in a spanning tree. Prim's algorithm starts with a single node and explores all the adjacent nodes at every step. The edges with minimal edge weights causing no cycles in the graph get selected. Hence, we can say that Prim's algorithm makes a locally optimal choice intending to find global optimal choice. That is why it is called as greedy algorithm. Moving ahead, let's understand how we can find out the minimum spanning tree using Prim's algorithm. Now, given a graph G consisting of vertices V and edges E, we need to construct a minimum spanning tree G' with vertices V' equal to V and edges E' equal to V minus 1, having the summation of edge weights minimal. This particular graph G contains 9 vertices and 12 edges. That means our MST G' will have 9 vertices and 9 minus 1 edges, that is 8 edges. So, with this in mind, let's create an MST for this graph G using Prim's algorithm. The first step in Prim's algorithm is to choose an arbitrary starting vertex. Here, we'll select node A as our starting vertex. Now, the next step in Prim's algorithm is to add new vertices with a minimum edge weight. In this case, From vertex A, we have two possible edges for traversal. The edge weight for edge AB is 1, whereas the edge weight for edge AC is 6. So obviously we'll choose vertex B here. Since we have reached vertex B, we will look into the possible edges for adding an edge with minimum weight to our MST. Edge BD have the minimum edge weight, so we'll add it to our MST. Now from vertex D, there is only one edge. Hence, we'll directly add that edge DH into our spanning tree. Now from vertex H, there are two possible paths, out of which the path HI has minimum cost. Thus, we'll add it to our MST. From vertex I, there is only one edge, so we'll directly include it in our MST. Now that I have included vertex G, I'm going to check what connected edges I have from vertex G. But since there is only one edge from vertex G, we'll just insert it on our MST. From vertex E, two edges are going to different vertices. So we will choose the one with least edge weight, and that edge is edge EC. Now that I have included node C, I am going to examine what connected edges I have to consider from vertex C. Currently, out of these two highlighted edges, I want to pick that edge which has not yet been included in MST and has the minimum edge weight. But the question that arises here is, can I add this edge AC into our MST? Well, we cannot. If we add edge AC to our MST, then it won't remain a tree structure due to the creation of cycle or a loop, which we cannot allow to happen according to the Prim's algorithm. Thus, in this particular case, we'll choose edge CF for insertion in our MST. And finally, the summation of edge weight for this MST will become 30. Also, till the time, you must have observed that this algorithm chooses the next vertex that offers the most prominent or immediate benefit. It started with an empty spanning tree for maintaining two sets of vertices. The first set was for the vertices included in the MST, and the other one was for the vertices that haven't been included in the MST. At every step, this algorithm considered all the edges that connected the two sets and picked the one with minimum edge weight from the adjacency matrix. A group of edges that connects two sets of vertices in a graph is called cut-in graph theory. So at every step of Prim's algorithm, we find a cut of two sets. One contains the vertices already included in MST and the other containing the rest of vertices. After that, we pick the minimum edge weight from the cut and include that vertex to our MST set. That is why this algorithm is called as greedy algorithm. Having said that, let's dive into the implementation strategy for developing code for Prim's algorithm. The idea behind Prim's algorithm is simple. All the vertices of a spanning tree must be connected. Hence, the two disjoint subsets of vertices must be connected in order to create a spanning tree. And further, these vertices should only be associated with the minimum edge weight to make it a minimum spanning tree. In order to store these vertices and edges, we'll create an adjacency matrix using 2D array in C programming language. Well, the indexes of this 2D matrix will be the vertices, where the values other than 0 will be the edge weights. For indexes 0, 1 and 2, you can clearly see that the adjacency matrix is having value 0. That means there is no recurring connection or loop for these vertices. So primarily, let's add them to our graph structure. For edge 1 to 2, we have the weight value 2. So we will add edge between vertex 0 and 1. After that, we have edge between 2 and 1. The value for this edge weight is 3. So we'll add edge between 1 and 2 and assign 3 as its edge weight. Finally, the edge weight for connecting 0 to 2 is 4. So we'll insert it in our graph as well. In the next slide, we'll discuss the strategy for implementation of a Prim's algorithm. From this example, I hope you are clear with how we are going to maintain a structure of a graph using 2D matrix. In the next slide, we'll discuss the strategy for the implementation of Prim's algorithm. The first step of this algorithm is to maintain a set for keeping track of vertices included in an MST. Once we create the set, we'll assign a key value to all vertices in the input graph. Initially, we are going to set all key values as infinite, and at the runtime, we'll assign weight 0 to the first vertex. By doing that, we choose it as an arbitrary starting vertex. Once done with that, we'll start adding vertices to our minimum spanning tree. For that, we'll pick up a vertex u with minimum weight to insert it into our set. After that, we'll also update the key values for all adjacent vertices of u. On that note, let's visit a code editor to implement Prim's algorithm using C programming language.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by SimpliLearn. Click on the link in the description to know more.
Now, in order to begin with coding implementation, we'll need to load some dependencies. For this implementation process, we are going to need a Boolean set in order to keep track of vertices included in our MST. That is why we'll include a standard Boolean library in our program. So, #include std bool.h. Once done with this addition, we'll define a number of vertices that we are going to use in our graph. I'm going to set the number of vertices to 5. So let's do that. Define vertices 5. And if you want to implement MST for a larger graph, then you must set the number of vertices to a more significant number. Now let's move to the main function. The graph that I'm going to use for generating a minimum spanning tree is supposed to be stored inside a 2D matrix. So first let's have a look at that graph. This is the graph for which we want to develop a minimum spanning tree. The first step that we must take to do that is converting this graph into 2D matrix. As discussed earlier, the diagonal values will be null or 0, and other values will be the edge weights between two nodes. So without wasting any time on this, I will directly create adjacency matrix for this graph inside our code editor. This part is about maintaining our graph in form of 2D matrix. Now, after this, we are calling prim's MST function, which is responsible for generating a minimum spanning tree. So let's do that here. Prims underscore MST, and we'll pass this graph to this function. But we haven't developed any code for this prim's MST function, but we'll do that now. So let's create prim's MST function, void prims underscore MST, and we'll pass graph as an argument. Should be vertices and vertices to make it a 2D matrix. Now inside this function, we'll create an array named key to store key values of all vertices. Int key vertices. Along with it, we'll also initialize the parent in which we'll store our actual MST and Boolean set to keep track of each and every vertex of our graph. So let's create that parent array. Vertices, and we'll create Boolean set for maintaining track of all vertices. Now after this, what we'll do is we'll set the key values of all vertices to infinity, and we'll also make sure that these vertices are not part of our minimum spanning tree set. So for that, we'll create a for loop, and inside this for loop we'll use iterator element I, and we'll initialize this element to 0 till vertices and will increase the iterator element I for each loop. Inside this loop, we will set key I to the possible integer maximum value, and in order to use this value we'll need to add one library which is called as limits.h. So we'll add it here, hash include limits.h. Okay. After this, we will also make sure that these vertices are not part of our minimum spanning tree set or boolean set. So for that, we'll write statement min underscore span underscore tree I should be false. That means empty. And we'll add indentation. Okay. Now in order to choose the arbitrary index, we'll set the key value of our first vertex to 0 so that it will be chosen first in our minimum spanning tree. For that, we'll write statement key 0 should be equal to 0. And as we have chosen vertex 0 as our first arbitrary vertex, so we'll also set the index 0 of the parent array to -1. By doing this, we are ensuring that the index 0 is the root node of our minimum spanning tree. Now to choose vertices with the minimal key value, we'll create a new function named least key. So let's do that. Int least underscore key, and inside it we'll pass arguments int key, boolean set, and inside this function body we are going to set all key values to infinity. So let's do that. Int list will be equal to int underscore max, and we'll also initialize minimum underscore index as new variable. Now using a for loop, we'll traverse through all vertices. If the given vertex is not present inside the minimum spanning tree set and the key value is also smaller than the least value, then we'll set the least variable to the key value and minimum index to that particular index v. So let's create that for loop, and inside it int v as iterator element, and we'll initialize it to value 0, and the maximum limit for this v will be vertices, and we'll increase the value of this small v variable plus. Now if the chosen vertex is not present inside minimum spanning tree set,
and the key value for that vertex is also smaller than list, then we will set list equal to key of v and minimum index to v, and we'll get out of this for loop and we'll return the minimum index value. On that note, let's arrive back at our primSMST function. Here, using a for loop, we'll fetch the minimum index that we have generated inside a list key function. So let's create for loop. We'll use count variable here and we'll initialize it to 0, and we'll move this count variable till vertices -1, which is nothing but the number of vertices in our minimum spanning tree. Next, we'll increase this count variable Now we have arrived inside this for loop body. Now we'll store that fetch minimum index value in variable u. So int u will be equal to list underscore key, and we'll pass key and boolean set, that is min underscore span underscore tree, and we will include this list node, that is u, to our minimum spanning tree set or boolean set equal to true. Now here we'll use a nested loop in order to insert a complete edge which is initiating from node 0. Inside this loop, we'll further call if log to validate some conditions. So let's create that nested for loop first. Int v is equal to 0 to v till vertices v plus plus and inside this for loop we'll add if log and we'll check graph u to v and mean span tree v is equal to false, and graph u v is minimum than key of v, then what we'll do is we'll set parent of v to u and key of v to graph UV. So now you must be thinking about what exactly is this code is doing. So actually what we are doing is we are inserting node U into our minimum spanning tree. And once we include node U into our minimum spanning tree, then we check if there is any edge between U and V. V is nothing but all the vertices inside the graph. If there is edge between U and V, then we check if that V is included in our spanning tree or not. If it is not included, then we check the key value of V. If the key value of V is greater, then what we do is we set parent of V is equal to U and key value of V is equal to graph UV, which is nothing but the weight between edge U and V. So that's what this code is doing. After this, what we'll do is we'll write one printf statement. So for that, we'll need to get out of this for loop and we'll write printf statement. Printf created spanning tree for given graph is \n, so that this next part comes inside the next line, and we'll also make a call to print underscore prims mst function, which is not created yet, but we'll write code for it once done with this call, and we'll pass parent and graph to it. Well, now let's create a code for this print prims mst function. Int print underscore prims mst, and we'll pass int parent, we'll pass int graph with vertices and vertices. Now inside this function, what we'll do is we'll write one printf statement to show the pattern of printing edge /t weight /n semicolon, and in next slide we'll create iterator element and we'll initialize it to 1 and we'll extend this till vertices and I++ printf modulus d dash modulus d /t \t modulus d and \n, and we'll pass parent I
comma I, comma graph I and parent of I. This statement will print a graph on our screen, but here is one mistake that I have made. I haven't added the indentation for this for loop. Okay, I think this should be fine now. We can say that our coding implementation is finished. Now let's run our code and check if it is working or not. Well, we have received output on our console here. That means our code is bug free and it works fine. You can verify this result by drawing the spanning tree of output on your notebook, and further, you can compare it with the graph that we have shown previously. Furthermore, if you're concerned about this code, then don't be, as we can send it over to you if you drop your email IDs in the comment section below. Additionally, you can also try to run it on your local system to understand its minute implementation details and implications. So with this successful coding implementation, we came to the end of this video.
And with that, we have reached to the end of day 2. So far, we have learned data structures and algorithms. On day 3 of this software development training week, we'll escalate things and get started with the whole programming language and learn object-oriented programming concepts. We'll use C++ as a programming language. So thanks for watching and don't forget to subscribe to stay tuned for more from SimpliCode.